I remind you that the Institute goes on for 3 more weeks, but let's start immediately with the first talk by Helvi Witek, talking about adventures of black holes.
Okay, thank you very much, and good morning, good afternoon, everyone. It's a great pleasure to present some recent work to you that is part of our program to model black holes and black hole binaries in extensions of general relativity that will allow us to test gravity under extreme conditions using observations of gravitational waves. I will highlight work that I've done in collaboration with Hector Riccardo da Silva, who is a postdoc at the Albert Einstein Institute in Potsdam, one of my PhD students, Matt Alley, who is still in the UK, and one of my colleagues here, Nico Yunus. And the second paper that I will mention was done in collaboration with Banafsheh Shiralilu, who is an excellent PhD student at the University of Amsterdam. So if you want to hear more about post-Newtonian calculations, you should invite her for a talk. And we worked on this together with Tanja Hindera, Samaya Nestanka, and Mr. Ortiz. Now, you've seen that I've slightly changed the title of my talk, and I've shamelessly adapted the title of one of my favorite collection of short stories, which are Arthur Conan Doyle's Adventures of Sherlock Holmes. And I'm choosing that, I'm inspired by that, because his book or his stories describe the scientific method like little else and was revolutionary at its time, even though we take that as a given today. And one of the quotes that I think can guide us somewhat in our quest to understand gravity in its extreme regime is the following. So in one of his cases, he says, well, it's an old maxim of mine that when you have excluded the impossible, whatever remains, however improbable, must be the truth. Now, and for us, we are kind of playing gravity detectives and trying to put all the pieces together, all the pieces of the puzzle together that would allow us to either exclude or support modifications and signatures of extensions of general relativity. Now, what are the mysteries of nature that we are trying to understand? And I would group them in 3 main topics. So one is a late time accelerated expansion of the universe. So that goes under dark energy and studies in cosmology. Another quest is that of dark matter, which makes up more than 80% of all gravitating matter in the universe. And still we are somewhat in the dark of what they really are. I'm not going to talk about this today, but there's actually also a program where we can use black holes to study a certain type of dark matter candidates known as axion-like particles predicted from string theory. And this program has been moved forward by people like Katie Clough or Vitor Cardoso and myself. And we are actually having a paper coming up with one of my other PhD students, Giuseppe Ficara. Now, that's the only thing I will tell you about this today. And I'm talking today about the idea that, one of the biggest questions I think we have in fundamental physics is what is quantum gravity? How can we consistently combine gravity and quantum physics? Now, I'm not a model builder, so I'm not presenting you new candidates for quantum gravity. I'm one of the people who says, okay, if you have a candidate for quantum gravity, if you take its low energy limit, what does it tell us about our theory of gravity? How does it extend general relativity? And how does it impact the dynamics of black holes and the resulting gravitational wave signal that we can now measure? So in some sense, I'm using black holes and gravitational waves as gravity detectives for new physics. Now, and I have to say that we now actually have data. So this is really amazing. Since the first breakthrough detection by the LIGO Interferometer Gravitational Wave Observatory, short LIGO, we have now about 50 events of black hole or neutron star mergers. So here I'm just showing you a list a plot of all the events that we have so far in the first 3 observation runs from 2015 to March last year. Here's a mass scale in units of solar masses. The yellow dots here are neutron stars measured with electromagnetic observations, so not with LIGO or Virgo. The orange dots here indicate neutron star mergers detected with LIGO and Virgo. And in one case, we also had this really strong electromagnetic counterpart, the short gamma ray burst, indicating that it's really a neutron star merger, followed by kilonova and radiation across the entire electromagnetic spectrum. Here in purple, we have black holes that we have known about before the LIGO detections. So candidates for black holes that we knew about from electromagnetic observations in the X-ray spectrum. And here in blue is this nice collections of black hole mergers observed with LIGO. So long story short, we now have the data that allows us to understand gravity in its nonlinear regime. So I think this is really exciting. I remember when I started out as a PhD student, that was still very far in the future. And there was still the sense of, oh, maybe one day we could detect it. And it's so exciting that we now are in an era where we actually have observational data to test and understand physics even more by combining theory and observations. So this is really exciting. And that said, so we have the data, but do we have theories? And in particular, if we want to test gravity, do we have theories that extend our standard model of Einstein's gravity? And the answer is yes, we have plenty, maybe too much even. And you may ask 3 different colleagues and they may tell you 6 different favorite theories that they may have. So we now are in a position that we actually have to take those ideas and make it possible to confront them with observation. That is, we need to have observational predictions. And that's exactly where my work comes in. So that's still somewhat lacking, although there has been a lot of progress over the last few years, where we say, okay, what are the observational predictions, especially if you want to compare to gravitational wave signals? Well, then we have to model the dynamics and gravitational radiation in compact binaries. So the inspiral merger and ring down of, for example, 2 black holes. Yeah, so that's what I want to do here. There are different approaches to do that. I'm an expert in numerical relativity. That is, I'm an expert in modeling the strong field regime of gravity that unfolds when black holes collide. That means I have to use supercomputers and large-scale codes to model these scenarios, but that also means I actually have to provide specific equations to the computer. So we are still thinking about ideas of how we can provide a code that is somewhat parameterized to cover a large range of theories. At the moment, we have to select one theory or one class of theories to do so. So today I will tell you about our progress in one class of theories that goes under scalar Gauss-Bonnet gravity or curvature squared type theories. And I will write down the actions in a moment. Let me just tell you why I'm interested in this type of theory. So first of all, this one can be shown to come about in the low energy limit of some string theories. So this theory is really inspired by some quantum gravity candidates. You would also get this type of theory if you take a Lovelock gravity. That is the most general theory of gravity in d dimensions that gives you second order field equations. So there's a hope to have a causal theory that is mathematically well posed as a partial differential equation initial value problem, which we have to worry about in numerical relativity. And if I take the pedestrian approach, so really what we're able to do by taking this theory is to have a good model that allows us to study higher curvature corrections that may become relevant in the strong curvature regime. So even, and I know if Ira is here, we had this discussion several times, I will only take the leading or the higher curvature term in the action to study precisely this effect here. Okay, so long story short, what is the action? It's written down here. So I'm working in 4 dimensions. We have the Einstein Hilbert term here, so just the Ricci scalar. We have coupling to a scalar field, gradient phi squared here, so this is just a standard kinetic term. And then we have a coupling term here highlighted in red, where we have this alpha GB is a dimension full coupling constant. It has a dimension of inverse length squared or inverse mass squared. Then in here, this curly G is a Gauss-Bonnet invariant. That is, it's this combination of the Riemann squared, Ricci tensor squared, and Ricci scalar squared. And this particular combination gives you second-order field equations. And then this f of phi here is a coupling function for the scalar field. And the specific choice of this coupling function essentially selects a subclass of this scalar Gauss-Bonnet gravity class of series. And I divide them up in 2 types. So this is not really done in the literature, but for the sake of this talk, I find it very convenient to talk about 2 types. The first one is the following, where the derivative of this coupling function with respect to the scalar field can never vanish. That's the case, for example, if you have a dilaton type coupling, or if you take a small field expansion thereof, or just say, okay, I demand that I have an additional shift symmetry, then you may have this kind of function. And in this case, as you will see on the next slide, black holes always carry scalar here. Yeah, so this type of series or these types of functions always lead to a black hole with a scalar charge. The second type is different. So here the derivative of the coupling function with respect to the scalar field can be 0 for a value of the scalar field. And that's the case, for example, if you want to study functions that go like phi squared or some Gaussian type of coupling here. And in this case, you can have both the Kerr solution of Einstein's equations as well as hairy scalarized black holes. And we will look at that in a bit more detail in the second half of this talk. Okay, so let's start. So what I will do for the rest of this talk is go over first type 1 and then type 2 type series, tell you a little bit about the properties of black holes in these subclasses and what the implications are for the in-spiral dynamics and the merger dynamics. Okay, so let's start with type 1. As I said, here's a coupling function. The derivative of the coupling function with respect to the scalar is never 0. Just for the sake of giving you a specific example, I will focus on the shift symmetric coupling. That is, the function f is just related to the scalar field phi itself. But all I'm saying in this part is also true for dilaton type coupling. And in this case, the scalar field equation can be written in the following form. So you have your wave operator acting on the scalar field. In general, this is the right-hand side. So you have here the derivative of the coupling function. That's why this is so important. And then you have the Gauss-Bonnet invariant here. That is, for black hole spacetimes, this essentially gives you the spacetime curvature itself. And if we have this shift symmetric coupling, this just becomes this coupling constant times space-time curvature. That is, if you even if you start with a 0 scalar field, so no scalar field in the beginning, and you have a black hole or you have a curved space-time, then this scalar field will always be sourced through this term here, through the Gauss-Bonnet invariant. People have found these solutions and have proven that black holes always have hair in this theory over the past few years. And the last item that I mentioned, so that scalar hair always forms dynamically, even if you start with a vanishing scalar field, is actually work that we have done a few years back together with Thomas Soterio and his then student Robert Benko in a numerical work. Okay, so that's what's happening for a single black hole. So a single black hole can always carry a scalar here, and it's actually so to leading order, it's a monopole scalar charge. Okay, so now let's think about what happens if we put that in a binary. Now we can think about that as two orbiting scalar charges. And that's something that we have studied actually numerically. So I've implemented the Gauss-Bonner field equations in a decoupling limit. That means the scalar field is evolved around the background that is GR. And I've implemented that in my numerical relativity library called Canuda. It's publicly available here, and it works together with the Einstein toolkit, which is an open source numerical relativity code for computational astrophysics and nowadays also fundamental physics in 3+1 dimensions. And this is work, so this first work that I want to advertise here was actually done a couple of years back together with Leonardo Gualtieri, Paolo Pani, and Thomas Soterio, where we studied the dynamics of the scalar field as sourced by a black hole binary. Here I'm showing you one example where these black holes had a mass ratio of 1 to 2, and the total mass is scaled to be 1. And what you will see in a minute is the evolution of the scalar field on the equatorial plane of that binary, and you will see how we will develop scalar dipole radiation due to these orbiting accelerated scalar charges. And what we will have here, just one last comment before I show the animation, black holes that complete about 10 orbits before they merge in the background. Okay, so let's actually look at this in detail. I hope you can see my animation. So what we have here, as I said, is the equatorial plane of our evolution. In the background, we have these two black holes orbiting. The yellow blobs here is the scalar hair around each of the black holes. So we have the smaller black hole here, so that gives rise to a larger scalar charge. This is a larger black hole. And as they orbit around each other, you should see now becoming more and more clearly scalar dipole radiation that is emitted throughout the inspiral, that is really driven by the dynamics of the background black hole binary. So that is the frequency and amplitude of this wave increases over time as we approach the merger. Now the black holes have merged. All the non-axis symmetric modes of the scalar field are dissipated away, and the final black hole settles down to an axis-symmetric solution with an axis-symmetric scalar field around it. Scalar here. Good. So that is just the inspiral, just the merger, and only the last few orbits, and only the decoupling limit, so the evolution of the scalar field on top of the black hole. Now the next question is, what happens in the inspiral? And that is a recent work that I said I would like to advertise a little bit more. So to cover the inspiral, you would perform a post-Newtonian type calculation, that is a calculation in power series of v over c, so characteristic velocity over speed of light. Early work in this approach looked at energy fluxes, or two-body Lagrangian and the sensitivities, so the difference between the scalar charges in expansion, not only about the post-Newtonian parameter, but also assuming that this coupling alpha GB over m squared, which is the dimensionless coupling, is much smaller than 1. In our most recent work with Banafsheh, Shira Lilu, Tanya Hindra, Samaya Nastanka, and Nestor Ortiz, we actually relaxed that assumption. We allow for general coupling constants here, and we've calculated the gravitational waveforms up to 1 pn beyond leading order here. So I know this is a very busy plot, so let me just talk you through that a little bit. What I'm showing you here in the middle is a plus polarization of the gravitational radiation as a function of time. together with the evolution of the frequency, the gravitational wave frequency, as a function of time. The black curve here corresponds to just the evolution in general relativity, and the blue curve here corresponds to the evolution in Einstein dilaton Gauss-Bonnet gravity here. So it's in the same subclass as type 1 subclass. We here are also looking at a black hole binary with a mass ratio of 1 to 2. The total mass we set to be 15 solar masses, and we picked this dimensionless coupling constant here. And time equals 0 here corresponds to roughly 10 hertz. That is when we would first see the signal in the LIGO band and how it would evolve through the band. So what you can see here in this first inset is that initially we aligned the waveforms so they agree both in amplitude and phase. You can see at intermediate late times here in yellow, this is the middle box, while the amplitude is still not too dissimilar, there has already been quite a phase shift. And at late times, the phase shift due to the emission of scalar dipole radiation that carries away energy from the system, that is, it accelerates the inspiral of our black hole, which then leads to a phase shift in the gravitational wave signal. So that becomes really rather strong. So you see here at late times that our black holes in Gauss-Bonnet gravity would merge significantly earlier. Now, one last item here. So I'm showing you here this example for the post-Newtonian waveforms for this type 1 theory. But Banafsheh has really done the calculation for also general coupling function. So we can also use this framework to study the second type, type 2, that I will talk about now. So type 2, just to remind you, in this case, the coupling function, the derivative of the coupling function, sorry, this is actually a typo that I meant to fix. So the coupling function that we're looking at is of the type phi squared, which means that the derivative of it can actually become 0 at some point. So in this particular case, this type of series would give you the following equation for the scalar field, slightly rewritten. So you again have your wave operator here. This is a general form of the coupling, but because it has this phi squared type form, we can actually rewrite this as a Klein-Gordon equation for the scalar field with an effective space-dependent mass term. And that gives rise to a quite interesting and broader space of solutions that I'm plotting here on the right. So here we have the coupling constant, now labeled as eta to slightly distinguish that from the previous one, in units of solar mass squared, as a function of the mass of the black hole in units of solar masses. If the derivative of the coupling function becomes 0, then the solutions of general relativity, that is the Schwarzschild and Kerr solution, still exist. So that would correspond to these white spaces here in the phase space. And in fact, if the effective mass term is larger than 0, these solutions are unique. Yeah, and that has been proven in the paper by Caio Macedo, Hector Carrera Silva, and collaborators. However, if the effective mass term squared becomes negative, that is, if this combination of the coupling function or its derivatives and the Gauss-Bonnet invariant becomes negative, then you can have a spontaneous build-up of scalar hair. So you get spontaneously scalarized black holes, and these correspond to these colored lines here in gray, blue, and red. And I should just mention that more recently, over the last year, people have also, so this, sorry, I should have said that. So this is actually the phase space for non-rotating solution. There's an additional way to induce scalarization if you have rotating black holes. So that goes under the name of spin-induced scalarization, because in this case, the Gauss-Bonner invariant can actually change sign as you look at different regions in space. So there the phase space is even a little bit more complex, but I'm not going to go into any details here. So for the rest of this talk, I will actually focus on black holes that are initially non-rotating. Good. So long story short, we have this mechanism that can give rise to spontaneously scalarized black holes. Now, the next question is, what happens in a binary? And that's exactly the question that we asked ourselves a couple of months ago when we started working on this. Bless you. We started working on this project. And we actually guided ourselves initially, at least, by information that we had from neutron stars in scalar tensor theory. So let me take a short one-slide break to tell you about neutron stars in scalar tensor theory, where there is a coupling between the scalar field and the matter in such a way that the scalar field can be sourced by the energy momentum tensor. This is a trace of the energy momentum tensor of our perfect fluid, of our neutron star matter. And there are cases in regions in parameter space where neutron stars can spontaneously acquire scalar hair. And here's just the solution space for that, for a specific equation of state for the neutron star matter. All I want you to take away from this is that there are scenarios where isolated neutron stars can spontaneously scalarize. Now, in this case, if you put those in a binary, and that has been studied back in the day in a series of papers in 2012 and 2013. So if you put two neutron stars in a binary, even if they are not scalarized, if the binary becomes sufficiently compact, you can have dynamical scalarization. So essentially sourcing the scalar field being sourced when the binary is sufficiently compact and dense. And that goes under dynamical scalarization. So the reaction here would be a not scalarized star plus a not scalarized star gives rise to something that's dynamically scalarized. Or you can have the scenario where one of the stars is not scalarized, the other one is scalarized, and this induces a scalarization near the merger and gives rise to a scalarized neutron star after the merger. So that's what we totally expected when we started our first simulations. And again, I fear we have implemented the extensions to study this type of theory in Canada in my library. We've performed the first studies thereof, submitted the paper at the end of last year, just before Christmas. And we again focus on the decoupling limit. So we have a black hole binary in the background and evolves a scalar field on top, which gives us the onset of scalarization. And we focused first, so that will be on this slide, on the simplest scenario where we collide two black holes just head on. And here we are looking at 4 different scenarios. Let me just tell you about the scenarios first that I'm indicating here in this Feynman type diagrams. So the in states are either unscalarized, so as bar plus unscalarized, mixed, so scalarized plus unscalarized, 2 scalarized black holes that lead to something that's not scalarized, and 2 scalarized black holes that give rise to a scalarized solution. Now, before I go and show you the time evolution of the scalar field here in this plot, let me actually show you another animation. I hope this will work. So in this case, as I said, we are looking at the head-on collision of 2 black holes. One of them is scalarized, the other one is not scalarized. And I will actually put this a little bit on, so I hope you can see this. So I actually put this on repeat because the animation is a bit short. So here you have the scalarized black hole and the unscalarized black hole. That is, we actually have unequal masses here, again, a mass ratio of 1:2. The white lines here are the isocurvature plots indicating the strength of the Gauss-Bonner invariance, the curve. So think of that as the strength of the curvature. And what you should hopefully see is that here the curvature is larger, so the high curvature region closer to the origin, so it's strong enough to support scalar hair, whereas in the other case, and in particular after the merger, the curvature becomes too low to support the scalar field, or the scalar hair. The scalar field just dissipates away, and we end up with just so in this case, a non-rotating, unscalarized black hole, so just a Schwarzschild black hole in this theory. Okay, and we find something similar for most of these setups. So here, if we look at the time evolution of just the scalar field monopole as a function of time, 0 here corresponds to the time of merger. And we see if we start with 2 not scalarized stars, the scalar field essentially never builds up, and we just gave a little perturbation that you can see here decaying over time. Then the other 2 cases, so here the one that I showed you, the scalarized plus not scalarized, and scalarized plus scalarized. If the coupling constant is relatively small, then the curvature is only, so the curvature just supports scalar hair before the merger, but after the merger, the final mass of the black hole increases, curvature decreases as it is inversely proportional, and the scalar field is no longer supported and just decays away to infinity. And in this last case, we cranked up the coupling constant, so the number that multiplies our Gauss-Bonner invariant so much that before the merger, the scalar field actually increased exponentially. And after the merger, the final black hole just barely supported the scalar hair. Okay, so that's what we found for head-on collisions. And by the way, if you're interested, you can find more animations and some more descriptions on our website and on our YouTube channel for the code, where we have collected more simulations for our project. So yeah, that was for head-on collisions. Let's take a quick peek at ongoing work for the inspiral. So in this case, I'm actually looking at black hole with equal masses. That means we can set up the system such that both initial black holes are scalarized. Yeah, so we have this scenario here. The black holes in the background complete about 10 orbits before merger, then merge and settle down to final rotating black hole. So let me try if this last animation works. It sometimes doesn't with Zoom, so if one of the organizers just can indicate if they can see the animation, that would be grand. So I hope what you can see.
Yes, you see it.
Okay, wonderful. So here, this is just half of the slice of the equatorial plane. You see here the scalarized black hole. Here's its companion. And again, in white, we have the isocurvature regions here. And it's, okay, so I hope you can see it. It's stucking a little bit. But what we want to see here again is these initially scalarized black holes that orbit around each other. The curvature regions here connect is actually also a very beautiful study of how the space-time curvature itself evolves during a black hole merger. And what you would see here, so the scalar radiation is not very visible because actually the color scale changes here, but what you would see is that there is scalar, in this case, quadrupole radiation. The dipole is suppressed because of the symmetry of having an equal mass binary. And then at the end, our binary now merges with strong scalar radiation here. And the final object starts settling down to something that becomes not scalarized. So here the scalar field dissipates as indicated by this decreasing scale in the scalar field. So if we look at this in the time, so mode versus time plot, so here we have again the scalar field monopole measured at an extraction radius of 50 m away from the system. So for those of you who are not familiar with numerical simulations, our numerical domains are finite size. So we measure radiation at radii of finite size away from the system. So this is here the monopole scalar field, the quadrupole scalar field as a function of time. And for comparison, we have the quadrupole mode of the gravitational radiation in the background, also as a function of time. Time aligned such that t equals 0 again corresponds to the merger. And now what we see here is a monopole scalar field, that is a scalar charge that we measure at a finite distance away from the two black holes, is slightly increasing over time. As it does so, and as our scalarized black holes orbit around each other, it excites a scalar quadrupole radiation. As I said, the dipole is suppressed because we have an equal mass binary, that is enhanced symmetry. If we had an unequal mass binary, we would also have the dipole radiation. But here, the quadrupole, again, the signal that we see is driven by the dynamics of our black hole background. And after the merger, the scalar field charge does decreases, so our black hole, final black hole, again, dynamically descalarizes. So in contrast to what we would have expected from the neutron star study that I mentioned as a break in between, we actually have the opposite effect, that in most cases, unless we really crank up the coupling constant, we find dynamical descalarization of the black holes. And that is a new effect that people have not quite anticipated in the literature before, that we are now studying in a little bit more detail, expanding the parameter space, expanding now also to study effect for rotating black holes, where you can have the spin-induced scalarization as well. But this is the first type of the study, and we identified this new phenomenon that we term dynamical descalarization. Now, to wrap up, let me just talk a little bit about observational implications, which is what I started out with. In the end of the day, we want to be able to make observational predictions and learn about our theory and either constrain or support it. So
just to tell you, you have 3 minutes plus questions. Okay.
Okay. So say that again.
3 minutes plus questions.
Past questions.
Yes.
Plus questions. Okay, no, that's fine. I'm almost done, as I said, so I'm just summarizing that here, and then I'll give you the overall summary, and I think we are absolutely perfect in time. So just to summarize the two different types that I looked at. So remember, the first class of theories gave rise to always have scalar here. So we always have scalar radiation before the merger that induces scalar dipole radiation, and eventually leads to a gravitational wave phase shift due to this additional emission of energy or additional dissipation of energy in the system. As you go through the merger and post-merger, your final black hole still carries a scalar here. That is, it also modifies the ring down signature. And people have already used studies, both of the inspiral and the merger ring down, to put observational bounds on this coupling. Now, I apologize to our high energy physicists here. So in the gravitational wave community, we typically write this coupling constant in this form. So the square root thereof has the dimension of length, kilometers. So the most recent bound was actually put forward just last week by Scott Perkins, who is one of our PhD students here in the University of Illinois, which is of this order. And the second type that I talked about here today is completely unconstrained. So as I said, we just identified a new phenomena that can happen if you allow for spontaneous scalarization. In particular, you may or may not have scalar radiation before the merger. If you do have scalar radiation, that would lead to a dephasing of the gravitational wave signal, and a lot of the arguments of this first type apply. If you do not have scalarization, then and you don't have this dephasing, it's hard to tell, or we are trying to work out if there's still, what we can actually learn about this, and when does the scalar field get activated? Is there anything that we can learn during the merger and post-merger? And again, what we have found in this particular case was that the final object was a black hole of general relativity. So all the scalar field was completely shed away. And the question is, does it still impact the ring down because the gravitational and scalar radiation decay on the same time scales, or is the effect much smaller than what we have in type 1? And what I just alluded to at the end of the last slide is that once you add rotation to the black holes, and in particular, if you look at inspiraling black holes that lead to a final rotating black hole, you may have actually spontaneous scalarization due to the spin. So this is really just the beginning of this study, and we are continuing here to understand just the phenomenology of those systems before we can even think about observational bounds. And with that, I guess the last minute, really just an overall summary. So I have looked at the phenomenology of black hole binaries in series where you have a coupling to higher curvature terms. And we saw that this gives rise to either hairy or scalarized black holes. I should also mention that you find similar effects for dynamical Chern-Simons gravity, where instead of having the Gauss-Bonner invariant, you couple to the Pointryagin density in the action. Now, before the merger, you typically do get a scalar radiation and a gravitational wave phase shift that has been used to constrain at least the first subclass of series. And then during the merger and the post-merger, you can either have a hairy black hole or you can have this new effect of dynamical scalarization. And the outlook, I already mentioned these two. So in the future, as I said, for this program, we are now trying to understand and really quantify the effects that you can get on the dynamics of the late inspiral and merger for black holes in Gauss-Bonner gravity, understand the ring down, understand the gravitational wave signal that would be emitted in these systems. And what I haven't listed here is once we have all that, we would of course perform a Bayesian parameter estimation and really confront this theory with observations. And with that, I thank you very much, and I will take questions now.
Okay, thank you, Helvi. Let's see. I see Claudia has already a question. Go ahead.
I was actually uploading.
Sorry? You were uploading.
Yeah,
no, I see.
Thank you.
I see there is Luke with his hand up.
Luke. Hello.
Yes.
So in your calculation in the type 1 theory, in your calculation of the waveform in the inspiral phase of compact object, do you use point masses for the objects or really black hole solution in this series? Because I would expect that the deviation from GR in this series should depend on the nature of the compact object.
That's absolutely right. So what we are using here is actually approximating basically as point masses that are scalarized. So we have used the sensitivities which indicate the strength of the scalarization that was calculated by Félix Julier a couple of years ago. So does that answer your question, Luke?
Yes, but I will think that the solution is different if you have really black holes, for instance.
So we haven't included finite size effects, if that's what you mean. So we do account. We do account for the scalar radiation because you're absolutely right. The black holes in this theory are different from the black holes in GR.
Okay.
Okay, there is time for another question. I see Claudia now really has a question. So Claudia, you can go ahead.
I guess I have a question related to what you just said. About the back reaction of the scalar field. Do you have an idea of whether it's negligible or it could be relevant?
That's exactly what we are trying to understand. So in the waveforms that I showed for the inspiral, you do have this phase shift precisely due to the back reaction from the scalar field. So in that case, so in the inspiral case, and that's, I think, the really amazing work that Banafshi has done here, we included the back reaction. We didn't do this order by order expansion that has been done typically before. And that leads to this dephasing that you can see in the gravitational waveform. For numerical relativity, it's much harder because there you need these well-posed initial value formulations. And there has been a recent work by Will East and Justin Ripley, where they took that into account for the first time in kind of a toy model. And all the other merger simulations are in this decoupling limit where you don't have back reaction yet. So we are working on that, and that's really more a mathematical question on how to formulate your field equations such that we can evolve them stably numerically.
I see. Thanks. But if you do an order back up in the envelope estimation, you would expect them to maybe contribute.
Yeah, I mean, we've actually played the other way around, that we said, okay, if we estimate what the next order contribution is, and we haven't observed it yet, then we can use it to put constraints on these series.
That makes sense. And can I ask you, this you can do, you don't need any coupling to matter, right? So presumably it's a case where this would be the most obvious observable of that field.
Yeah, exactly. So this is actually the fun part here. So here you really get new black hole solutions. So you don't need to play around with neutron stars. And in that sense, it's also complementary to studies that people have done, for example, in scalar tensor series where you need to have matter. Yeah, and here the reason is that you source the scalar from the curvature itself, so you don't need ordinary matter.
Yeah, that's really interesting. Thank you.
Okay, so we are running late, but let's squeeze in the last question from Alessandro.
Yeah, hi Helvi, sorry. Very quick thing, because you talk about ring down, but I don't see, I haven't seen any plot. Could you just give me an idea of how different are things? And in fact, what kind of constraints are put? So if they are put on only on, let's say, quasi-normal mode excitations, or on the full post-merger phase, everything, because without a plot, I don't get a sense of how big are the differences.
I focus, so you're absolutely right. And in the plots that I showed you, I focused mostly on the inspiral and merger. I didn't zoom into the ring down from the numerical simulations. So here what you would see is actually modulation of the signal as it rings down, because, so at least in this type 1, I've seen that for the scalar field, Masha Okunkova has gone to second order in expansion in the theory, and she also found a modulation in the ring down signal.
So
the
you
constraints that Alessandro, just to follow up on the constraint question, so the numbers that I gave you actually focus on the inspiral only. So what Scott and collaborators have done here in a nutshell is to say, okay, LIGO has this data and they have these parameterized constraints on certain coefficients in a parameterized post-Newtonian expansion. Now we can also use our other expansion, post-Einsteinian, where we know how the coefficients map from our parameterized expansion to the theory. And they essentially translated the constraints that LIGO got on the non-GR parameters to their scheme, and that comes from the inspiral, as you know. So we haven't actually done any of the constraints from the ring down, right?
Okay. Thank you.
Okay, so thanks again to the speaker, and let's move on to the next, which is, thank you again, which is, next speaker is Riccardo Sturani. Can you share the screen, Riccardo?
Hello, everybody. I'm trying right now. Let me see.
Okay, we can see it. So the floor is yours.
Okay, thank you. Let me just put presentation mode. Okay, I hope you can see the full screen, and I hope you can see my pointer as well. Do you?
Yes.
Okay, good. Since you answered my question, then you can also hear me. Okay, so thank you very much for giving me this slot, for letting me talk about some recent work. I have a disclaimer. I have to apologize for not being able to participate in the Slack channel on Relativity, and not being able to follow most of the talks actually. But my kid is out of school since 13 months now, and still I have all the teaching and all the usual stuff. So it's it has been a tough period, and it's not going to end soon here. Anyway, let's talk about more fun stuff, which is post-Newtonian and near-far zone interplay. So I kind of go back to the topic which has been touched upon earlier in this week. And basically the main result of this talk are presented in this recent paper by March, which is the natural prosecution of a paper of 2 years ago. And the idea is to tell you, I mean, how post-Newtonian approximation works from the effective field theory point of view, to go into some detail of how it works, why it is so powerful, and what are the limits. Okay, so this is the plan of the talk. By the way, I have 45 minutes, right?
Yes, you have 40 minutes plus questions.
Good.
And I will stop. I will tell you at 5 minutes before.
Thanks. So basically the main topics I want to cover, which are kind of non-standard, is the near-far zone interplay. I will tell you, of course, in a second what I mean by near and far zone within the post-Newtonian approximation to the two-body problem, and what is the choice of boundary condition of green function, which has some kind of non-triviality. And then I will give short updates on the most recent results that can be obtained with this approach. So I will try to convince you how post-Newtonian is, how and why post-Newtonian is useful. So for instance, let me digress on post-Minkowskian to start with. So we heard about post-Minkowskian, and we know that in post-Minkowskian approach, computing effective potential is not the most efficient way to compute the dynamics, but let's suppose we want to compute effective potential in a post-Minkowskian way. So what we have to do at the first post-Minkowski level, we have to exchange one gravitational mode between the two particles. So, you take the propagator, which has the appropriate polarization projector, and then you contract with the two sources, and then you have the green function. And here I purposefully left ambiguous what is the prescription of the green function. I just write epsilon term, because this will be the topic of the second part of the talk. So you do this integral, and you see, and you plug in here at first order, you can just put in straight lines, because anyway, this is already order G, and then you get the first post-Minkowskian correction. Then it is very hard to go to higher order in this way, and of course we know there are better ways to go to higher order than computing effective potential in the post-Minkowskian, but let's pretend we want to just to compute effective potential. So we know that scattering amplitude method or effective field theory boundary to bound technique have been already reached the precision of 3pn. Some part of the 4pm has been computed. I mean, we had, and the 4pn on the other hand has been computed by other method, the syncretic tutti-frutti method. So I will not talk about PM anymore in this talk, but my approach is the post-Newtonian approximation within the effective field theory point of view, which is also known non-relativistic general relativity, that has been pioneered in a seminal paper by Eyre and Walter in 2005. And if you don't like the name, well, I'm sorry, but non-relativistic general relativity looks like an oxymoron, but it was kind of borrowed from non-relativistic QCD, where it would raise less complaints probably. So what happens if you try to go this way to higher order in the post-Minkowskian approach? So for instance, you go to G squared. So you have this coupling. Of course, gravity is nonlinear, so you have a cubic coupling. And so, for instance, we have to put three propagator, 1 over p squared, 1 over p minus k, and k squared. These are real 4-dimensional propagator. Each one with its boundary condition. And so and the point is that here particle B has to interact with particle A at 2 different times. And then if you just want to integrate over the loop momenta, then you get this complicated function. And this intricacy, of course, gets amplified at higher order if you want to compute the effective potential. How this is simplified in the post-Newtonian. When this post-Newtonian, there is this major simplification that allows to make the integral much easier to compute, is that the propagator, here the green function, is expanded, because when we consider conservative effect, we expect the two particles, the two body exchange momentum, but not exchange energy. For k naught is much more than k, and you will see in a second that k naught is actually of the order of v squared times k squared. So we Taylor expand, and then of course we can really forget the epsilon. So it doesn't matter that I didn't specify what are the boundary conditions, because this propagator never goes on shell, so the epsilon is immaterial. And when K naught is the dependence on K naught is factorized, it's all in the numerator. Integrate first K naught, and basically the integration K naught just gives you delta function. And so one outcome of this, if you like, brutal approximation is that interaction becomes instantaneous. You see you have the delta function on particle A, particle B, but you have all kind of Taylor correction due to the derivative of the trajectory of the particle. Of course, this introduces an error. For instance, we are neglecting all the effects when the gravitational mode goes on shell, when K naught is of the order of K. So these are basically we are considering only the effect of longitudinal modes, not of the modes that can become radiative, which are being exchanged. So what we have done, so basically to tackle the difficulty of doing this integral, which has a non-trivial numerator and a non-trivial denominator, we expanded this four-dimensional denominator into separating the time part from the space part. What you could have done also was to expand the numerator, so give the denominator intact and expand the numerator. So when you expand the numerator, you're doing the multiple expansion, you see, because here you have a mass of the particle, and then mass times power of x gives you multiples, and the k gives you the derivatives. So these are expanding the exponential, the space part of the exponential, naturally leads you to the multiple expansion. One nice thing is that, okay, for instance, now you have to be careful about the boundary condition. And what I will argue is that you have to put in advanced retardant boundary condition, even if you compute time symmetric potential. The time symmetricity just come out of adding over possible orientation of the exchange gravitational modes. And here I wrote down explicitly the direct space shape of advanced retarded Green function, just to show you that they are real. They are real, and that means that their Fourier transform satisfies the reality condition. This is not true for the Feynman. The Feynman is complex both in Fourier space and in direct space. So we are moving, taking this approximation, basically expanding this exponential physically means that we are doing something brutal. So instead of looking at the two particles as two word lines, we are collapsing the two word lines to one single thick word line, and we are considering this thick object made of having a lot of hair, a lot of multiples. The nice thing, though, is that the parameter of expansion is basically the same of the other approximation of the expanding the denominator, say. The expanding denominator, which corresponds to the near zone, gives you a dynamic in expansion of v squared. Here, this kx, which is the small parameter, since k is of the order of the radiational mode, k is order of v over r, x is of the order of the size of the source is order r. So this parameter of expansion is v. So it's kind of the same of the near zone one. So time symmetric process is obtained by symmetrizing over propagation of gravitational modes. And what one usually read and says is that longitudinal modes are integrating out in the near zone, and the far zone only cares about, sorry, my laptop is out of power. Yes. And the far zone only cares about radiation. Well, this is not quite true, because you see here in the multiple, you don't have only radiative multiple, but you have also mass, angular momentum, and they do. I mean, they are source of longitudinal modes, and these longitudinal modes in the far zone, they do play a role in the dynamics. So the far zone does not only deal with radiation modes, but also deal with the longitudinal modes sourced by multiples, by conserved multiples. So there is a really qualitative difference between conserved multiples that source longitudinal modes and radiative multiples, and multiples which are not conserved that source real gravitational waves. So this separation in near and far zone is nothing but something, it's an old acquaintance in particle physics. I mean, it's nothing new. And it's in particle physics, it's called method of regions. So just to give you an idea, the two theories, the near and far zone, are very different. So for instance, if you write Feynman diagrams So you get something like this for in the near zone. So you have two particles propagating in a separated world line and then exchanging all sorts of longitudinal modes with corrections, and the retardation effects are taken into account by the Taylor expansion that I told you earlier. Whereas in the far zone, you have a thick line parameterizing the degrees of freedom of the composite object, and this composite object can interact only with itself, so it can emit and absorb longitudinal modes and radiative gravitons in all sorts of interactions. You might also consider emission of radiation to infinity, so you can consider time and symmetry process, but this will not be part of this talk. I mean, of course, you can do it, people have done it. I just I'm gonna talk about it. So I will concentrate on this kind of diagrams. Now the point is, the control this approximation. So we have two approximations at our disposal. Each of the two is good in one of the, if you are describing some kind of physical processes, which is the exchange of longitudinal mode, and the other is good if you are focusing on the exchange of modes sourced by the multiples of the composite system. So which of the two should we use, and how far each of them is from the full post-Minkowskian integral? So the answer is very simple, but it's not trivial. The answer is that if you sum the two, then you get the exact integral you started with. So let me show you how it works in a very, very simple example of exchange of one gravitational mode. So you have in the full integral and the full Minkowskian integral, you have the full propagator, the full Green function, and the full exponential. In the near zone, you have the full exponential and the propagator expanded. In the far zone, you have the full propagator, the full Green function, but the exponential expanded. And then we can introduce a doubly expanded term, in which I expand both the exponential and the propagator. Okay, so and let's look at the difference between the full post-Minkowskian integral and the sum of the near and far zone integrated over all momenta. So you see, this might be counterintuitive because the near zone is supposed to describe the system only for hard modes, and the far zone is supposed to describe the system only for soft modes. But nevertheless, if I integrate the near and the far term over all of the region of the momenta and the sum, I will show you in a second that this is equal to the full post-Minkowskian integral integrated over the complete region. So let's suppose that the system displays a clear separation of scales. So there is the scale of radiation, which is soft, and the scale of longitudinal mode, which is hard. I decided that there is a hard zone for momenta larger than this kappa, and soft region for momenta smaller than this kappa. And then I split the integral in a hard zone and a soft zone. And then I add by hand a term integrated over all space, which is proportional to this doubly expanded term. The doubly expanded term, you see, it's completely factorized, the dependence on k. And we know from dimensional regularization, the integral of k to any power is 0. So we can add it for free. But then look at what happens. Then I put, oh, sorry, there is a typo. Yeah, this should be I and this should be I2. Sorry, this PN remnant from previous version. So here I get, in the hard zone, I get E minus N minus F minus D, and the same I get in the far. But in the hard zone, I can approximate, it's correct to approximate the full integral with N, so this is 0. And then again, the far integrand and the doubly expanded integral are the same in the hard zone. In the soft zone is the same, but the full integral is the same as the far integral, you see, because the full integral is this one, the far integral is this one. In the soft zone, it is okay to approximate the exponential, so the difference of these two is 0. And again, n minus d is 0 because in the soft zone I can also expand the exponential, and n is equal to d. So you see here, the far zone is good approximation to the full integral. Here the far zone is good approximation to the full integral. The sum of the two over all of the space is equal to the full integral over all of the space, and so this is 0. Okay, this argument can be extended to higher order, and I will do it in a second. Just let me tell you that if you go to higher order, there is a qualitative distinction that we have to make. So we've just, I hope I just convinced you that the full post-Minkowskian integral is just equal to the total sum, to the sum over unrestricted integration of the near integral and of the far integral. So in the near integral, so you get the potential, and then you get all of the correction, which are kind of this retardation effect. In the far zone, what you do, the lowest order diagram that you can think is the emission of one radiation mode and the absorption of a radiation mode. You cannot emit and absorb, I mean, you can emit in principle longitudinal mode that you can absorb it, but of course the result is zero because we will involve some derivative of the source, and the source being constant, then it will give you zero. So to get the first non-zero diagram, you have to put here non-conserved source, and if you compute this simplest diagram,
Riccardo,
yes, hello, yes. If you compute, can you hear me?
Am I the only one who doesn't hear Riccardo anymore?
Hello, I'm hearing you.
Okay,
hello?
Okay. It was just a second. Let's go on. Sorry.
Okay, so this is the simplest integral that you can write in the far zone, where, as I said, I don't know if this was heard, that you have to put non-conserved multiple moments, because if you put conserved multiple moments, so since this result is proportional to the derivative of them, then you will get zero by definition. So, but actually, when you get, even if you get you put here non-conserved multiple moments, this diagram is also zero because it's a total derivative. So you put in advanced retard propagator, and then you get q double dot with q triple dot, which is total derivative, which is zero. The imaginary part is zero if you write it in terms of advanced retarded Green function. You can write it in terms of Feynman Green function, and then you get a bonus result, which is you get via the optical Tion the right emission, the right, I mean, energy loss from this process, from the imaginary part. Then you can go to the next, to leading order, which is actually the leading order for non-zero result in the far zone. Yes, I can hear you. I can hear you.
I'm hearing Riccardo fine.
Okay, sorry. Sorry, it's me.
Okay, so the lowest non-zero far zone diagram is this one, where I put two radiative modes, because otherwise they are hit by derivative and they give zero. And here I can put a non-radiative modes, or I can put a radiative mode as well, but of course the leading order is by the non-radiative mode. And then the result is the famous tail integral. As I told you, the parameter of the expansion in the Lagrangian in the multipolar expansion was V, but when you introduce interaction, then you get a G Newton. Of course, you raise in G Newton, and basically the parameter of the expansion of this kind of diagram, where I keep increasing interaction, is Gm times K naught, which by Kepler's law, K naught is just the inverse of the period of the orbit, and so it gives you V cube. So basically, these far zone diagrams, they go in V cube, V cube, V to the 6, V to the 9, and so on. But of course, each of them receives post-Newtonian correction, because each of these sources is the finite leading order, and has V square, V to the 4, V to the 6 correction, each of these sources. So, and this to remind you, the mass coupled to them without derivatives to H00, a longitudinal mode, the angular momentum couples with one derivative to H0I, another longitudinal mode. So it's V square with respect to the mass coupling, because there is a V in the angular momentum, and there is a derivative here. And the quadruple, which is the leading order non-constant coupling, couples with, again, like with two derivatives. So like it's a V square. So it's a V square suppressed with respect to the mass coupling. Okay, now that I given you this outlook of the topology of far zone diagrams, I can go back to our near far zone splitting and see if it's true in the first interaction order that, again, the post-Minkowskian integral is equal to the near integral plus the flux plus the far integral. And here the post-Minkowskian integral involves three propagators. I mean, there's no diagram with just two propagators, so we move from 1 to 3. So we have three propagators in the full post-Minkowskian integral, and what I want to show you is that this is equal to integral completely calculated in the near zone plus an integral completely calculated in the far zone. So this is with the expanded the propagators, and this is a diagram with all the terms with expanded exponential. Of course, there is a delta because it's a two loop. There are three momenta, three propagators, but only two are independent. So first observation, I can split trivially the integral region into a hard region. Each of these letters refers to each of the three momenta. A soft region, and then there are mixed region. HH soft plus permutation. H soft, of course, cannot exist because of momenta conservation, because only one hard momenta wouldn't fulfill the momentum conservation with two soft momenta. So the H soft does not exist. So there is basically one fully hard, one fully soft, and one plus permutation hard soft. And here again, I can add at will a doubly expanded term, just because the doubly expanded term, all momenta dependence are completely factorized, and then in dimensional reduction, the integral will be 0. The integral over the whole space, of course, not the integral of D in each of these subregions. So what I have to check is that each of these three goes to 0. And this is easy to check, like in the leading order case, that in the hard region, so the full post-Minkowskian is equal to the near term for all the three propagators, and the far term is cancelled by the doubly expanded term. Equivalently, in the soft region, the fully post-Minkowskian is equal to the three green function, all of them in the far expanded way, and then I cancel the near expansion with the doubly expanded one. So here I'm fine. Here it's a bit more tricky. So because it's a hard soft region, so what I do is I have to play. I can substitute the fully post-Minkowskian integral with the near integral only for two momenta, and I can substitute with the far expanded term only for the third one. So, and then I do the same for the fully post-Minkowskian. I do for the n cube, which is the near expanded, and then for the far expanded. Then I get this usual relationship for, you see, the first factor is always for the hard, and the second factor is always for the soft. And so at the end, this delta is not variation, means the conservation over momenta. This delta means conservation moment. After all the simplification undone, I'm left with the double near term minus doubly expanded times f minus d. So again, I can now this is simplification is that since this term is while now I can extend the integration region from soft to all of the space and from hard to all of the space, because what I'm adding is 0. So I'm with this, I get the same integrand, but now integrating over all of the space. And over all of the space, the cube is 0. And also the integral of each of the d is 0. And so I'm left with this n and f. Basically, what I showed is that the difference, the error I'm taking by adding a fully near zone integral plus a fully far zone integral and checking it with a fully post-Minkowskian integral, this error is of this kind. But now, what I see is that the p dependency has been completely factorized, remember, because these n propagators are factorized. The only propagator which is fully post-Minkowskian is the one in the far zone one. So the only dependence of p, which is the third momenta, which is not factorized, is in the denominator of f. But since, so basically you have to do only one integral over this momenta, but doing only one integral over this momenta gives me back this integral, where I integrate basically one propagator over one momenta. And this is purely imaginary. So basically this is a correction to the flux. It's not a correction to the conservative energy. And so basically I sketch you the demonstration of how I can approximate the post-Minkowskian integral by the approximation, by the near zone approximation plus the far zone approximation, each of the two integrated over all of the momenta. So this might sound counterintuitive, no? Because we know that the near regional approximation works only for hard momenta, and the far regional approximation works only for soft momenta. But if I integrate over all of the region of the momenta, each of the two approximation, and then I add the two of them, this gives me back the post-Minkowskian integral. Okay, but I have one big gain, is that the integral in the near region and in the far region are much, much easier than the integrals in the full post-Minkowskian when I want to compute the effective potential. Okay, now, sorry, this was a bit technical, but this was to show, I mean, this was not invented by us, but basically we readapted derivation in particle physics that show that this method of region works to approximate the full integral. Okay, and then let's go back to the, just for a second, to the fully post-Minkowskian integral. If you want to compute this integral, for instance, then you get into this complicated function that mix p and x. But after near-far breaking, then we know that we can break the denominator, we can make it much easier, but we have a price to pay. So you see, oh, sorry, here I call it omega, what I meant was k0. So this is, you see, I have two momenta in the numerator because of this vertex in general relativity has two momenta, and then I have three propagators for the three internal lines. I do the expansion like I do in the near zone. You can think, okay, I know that the near zone plus the far zone give me the complete integral. I know the near zone is easier than the complete integral. The far zone computation is easier than complete integral. I can just go and do it. Yes, but there is some caveat, is that when you do this, you see here the power of k denominator increase at will. You can have arbitrary large power, whereas the denominator you don't have arbitrary. You also have power. You always have a term with only two powers. Okay, why? Because this omega you traded as a derivative, and you see, and you always have a derivative hitting the trajectory, and then you always have a term with only two momenta, whereas at the denominator you have increasing power of p's. This is bad because it will give you infrared divergences sooner or later, because you keep increasing the moment of p denominator, whereas you always have a term with two p's in the numerator. I mean, so this infrared divergence is nothing to do with the infrared divergence of gravity, just an infrared divergence put by hand by this approximation. This approximation introduces a spurious infrared divergence, which is due to the breaking this integral. If I knew how to solve the full integral, I wouldn't see this. But this is a mixed blessing because, okay, it introduced divergence, which is not physical and shouldn't be there. But the nice thing is that it's it gives you a highly non-trivial consistency check, because since it's not in the full theory in the first step, and we introduce by this breaking, well, when I add the near and the far zone integral, it should go away. And in this has been checked explicitly by us, that the near the far zone UV and the near zone infrared cancel each other, and we get a finite result. The logarithms do not cancel, the logarithms are physical, but the arbitrary mu scale in the logarithm do cancel. So you see, this is, suppose we only saw, I like to think in this way to this problem. Suppose we only had the far theory, which is the theory, the low energy theory, and we didn't know its UV completion, which is the near theory. Then it would be natural to hit ultraviolet singularities. And ultraviolet singularities, I mean, I just tell you that your theory is not complete at a short distance. There's nothing wrong with the theory. Then you see, you would get the singularity and you would renormalize it. In this case, since we know the near theory is the UV completion of the far theory, we just add it, and we don't need to do, I mean, we don't need to do any renormalization. I mean, we just regularize because the sum of the two is finite, and we get the physical laws. One thing, you see, this is the far zone contribution, which is in terms of the multiple, and this is the near zone contribution, which is in terms of individual word line. But the two exactly match. What about the imaginary part that comes from the far zone? In the near zone, there's no imaginary part because, as I told you, when you expand the propagator, the epsilon can go away. The imaginary part, it depends if you use Feynman or advanced retarded propagator. If you use Feynman, it's there, but anyway, it doesn't contribute to the classical potential, which is time symmetric. So I can just discard it, this imaginary part. I will tell you later what's the right thing to do. This is not the end of the story from the point of view of divergences, because the near zone has also honest UV divergences. These are due to the fact that you're modeling your black holes by points, so this is nothing strange again. But the nice thing is that all these UV divergences, they can be absorbed by counterterms, and these counterterms are zero on the equation of motion, so they're really not physical. And anyway, it has been shown that in other gauges, the UV diversity doesn't show up anyway. And of course, there's no IR divergence in the far zone, because the far zone is already the theory short at a long scale, at a small energy. So it's not supposed to have any IR divergence if it wants to describe real gravity. One game you can play is that forget the near zone, forget the UV completion, forget that you know the UV completion of the far zone, just take the far zone, it has a UV divergence, apply standard normalization group flow, and you get a prediction for the leading logs of the logarithms of the energy, for instance. And we have played this game based on previous work, and we have found complete agreement with the, for instance, extreme mass ratio result. With the difference that the normalization group flow results are non-perturbative in the sense that they work at any perturbative order, whereas the extreme mass ratio result were re-expanding the PN up to some ridiculously high order, but not infinite. Okay, now I touched upon a few times during this talk. Let's talk about what are the right boundary conditions to use if you want to compute the effective potential, the effective time symmetric potential. Contrary to expectation, there are really advanced retarded boundary condition. Why? Because when you are in the far zone, as I said, in the near zone, it doesn't matter because gravitons never go on shell, the epsilon term are completely irrelevant. In the far zone, when you have the full propagator, when you have the I epsilon in your propagator, you have to decide what are the boundary conditions. And of course, these are deciding the boundary condition is something different than solving the equation of motion. Okay, so in this sense, we don't need to use the Keldysh doubling because that has been engineered to reproduce the appropriate equation of motion. So what we do is take the Lagrangian, we derive the equation of motion, and then on the equation of motion, we substitute, or in the equation of motion, in the diagram, we substitute the upper boundary condition. I mean, radiation modes are emitted and then absorbed. So you just average over all possible orientation, and what you get for this propagator is 1/2 of G advanced plus G retarded. If you go to page 29 of these slides, it's not a typo. There are more than 27 pages. That all the background material of these slides, I don't count it in these 27. And then you check that the average of retarded advance exactly equals the real part of the Feynman. So the real part you get the same if you use the Feynman of the physical prescription of retarded and advance. But the Feynman is different. It has also an imaginary part. It is actually the part that allows you to fulfill the optical theorem. So in the case of exchange of only one gravitational mode, you can use indifferently retarded or advanced, but you have to be careful. If you use retarded and advanced, you have the right thing to compute the time symmetric potential. If you use Feynman, you compute the time symmetric potential plus via optical theorem, the emission flux or probability loss. You multiply by 1K, you get the energy flux. Then diagram with two full propagators. These are three propagators, of course, because there's no diagram with two propagators. But I say two full propagators because one is sourced by conserved multiple. So a conserved multiple has no derivative. So this propagator is like if it was near expanded. I mean, there's no k0 in this propagator. It's not 1/k squared minus k0 squared, just because the k0 would be the k0 of the Fourier transform of this source multiple, and this source multiple has only supported k0 equal to 0. So despite having these three propagators, only two of these are fully propagators, and the right prescription is to use sum over all possible orientation. One is G retarded, so the emitted here and absorbed here, and then you sum over the other orientation, and so emitted here and absorbed here. And if you do this thing, you realize you get 1/2 GR squared plus G advanced squared. But then you realize that the real part of the Feynman square is exactly the same as GR squared plus GA squared. And so you're okay, either of the two, to compute the conservative contribution to the conservative energy of this diagram. With the bonus that if you use G Feynman, you get also to get the imaginary part, which is related to the dissipative piece of this diagram. So you can think, oh, fine, then why using retarded advance? If using Feynman is the same thing for the real part, and on the top of it, I get the bonus of computing the flux. Well, this game only works if you have only two full propagators. If you start having three full propagators, like in the memory case, emission, and absorption, what you have to do in the correct physical prescription, so two are retarded and one advanced, and then you sum over permutation. But this is, for instance, you cannot have 3 advanced or 3 retarded, no? Because energy cannot disappear here or being emitted here. And the product of 3, at least to the best of my knowledge, is not, we cannot express this as the product of 3 Feynmans. Okay, so this nice trick that you can either use Feynman or advanced retarded for 1 full propagator or for 2 full propagators doesn't work when you have 3 full propagators. When you have 3 full propagators, you really have to follow the physical prescription of having 1 emission, 1 absorption, or 1 emission and 2 absorption, but you cannot have 3 emission or 3 absorption. Okay, so if you do the right thing, here you also, by the way, you also get that this diagram is finite, and this funny thing is that the diagram is a two-loop self-energy integral. Two-loop self-energy integral, we know they have divergences. So what happens to the divergence here? Well, it happens that they cancel in the contribution of different polarization. Of course, this is a gravitational mode. They can be polarized in all possible ways. If you compute an arbitrary polarization, you do find a divergence, which is proportional to the standard two-loop self-energy master integral of QCD, for instance. But when you add all of the polarization, then you get 0 divergence. Okay, so I can probably wrap up in the...
You have 5 minutes plus questions.
Okay, no, but I won't even use that. So where did we get with the NRGR to get the Post-Newtonian? Well, not we, but this German-based group, which I didn't see any of them in the talk, so I took the liberty to summarize in 2 lines what they obtained. So they computed the full 5PN result for the near zone. They computed a ridiculous number of diagrams. Of course, it's automatized. So they get all of the near zone result. They recomputed the far zone that we had computed earlier. So the sum of near zone and far zone of 5PN gives the complete 5PN result. One nice thing is that near zone doesn't have any divergence proportional to Riemann square, so black hole must still look for law of a higher order. So Riemann square would have been signal of a tidal deformation of black hole, and this would appear in the near zone computation as a UV divergence in the near zone proportional to Riemann square. This doesn't show up because all divergences are 0 on shell, even at 5PN. That means that if you want to see some tidal effect, you have at least to go at higher order with the Riemann dot square there, at least, or maybe more. So the 5PN far zone diagrams that contributes are the tail that already contributes at 4PN, but of course gives you a contribution at 5PN. There is here the longitudinal mode can be sorted by mass or angular momentum at 5PN, and then there is a genuine there is a diagram which is leading order at 5PN, which is the memory, where all 3 insertions are dynamical multiples, not conserved charges. And in our paper, you also find the expression from the UV divergence of the far zone for all multiples at G order square. So for diagonal of this topology, so now you have all the far zone UV divergences. Why that's interesting? Well, because if you go at higher order and you compute Post-Newtonian in the near zone at higher order, you will hit these infrared divergences, and you want to be sure as a consistency check of your computation that that they go away with the far zone. And the far zone one you already have. Just open this paper. Okay, and so these are the results. So you get the tail from the tail, which is a 1PN correction of the quadruple with the finite piece. Sorry, it's important to know that this prescription gives you the finite piece right. So there's no ambiguity in the finite piece. There would be ambiguity in the finite piece if you only look at the far zone. If you only look at the far zone and then you regularize, like you do in particle physics, no? You have UV divergence, then you regularize, and then the finite piece you cannot trust. It depends if you use one subtraction scheme or the other, and then you fix it by experiment. Here, provided you use the same regularization both in the near zone and the far zone, then you can predict also the finite piece, simply because in the original theory there was no divergence at all, so this finite piece is physical. And then you get the tail from the octuple, the tail from the magnetic quadruple, which are divergent. And then the divergence, the logarithm are of course related, but what is nice is also the imaginary part has the same coefficient of divergence. So basically from the logarithm of the conservative part, you can also get the flux. But the flux, you already know from Thorne formula. So basically the logarithm is fixed by the flux. And this is a contribution, for instance, this is a contribution to the energy at 4PN, and this is the flux at leading order. Okay, and then you also get the contribution of the tail of the source by the angular momentum, not by the mass. This is not divergent, so it doesn't give any contribution to the flux. And this is the memory. Okay, here I put the imaginary part as per the prescription of the Feynman, just because I have the bonus information about the flux. The tail with an angular momentum instead of mass source with the longitudinal graviton is not divergent, doesn't contribute to the flux, and also the memory doesn't contribute to the flux. And it has these results. That is this is you see this asymmetric mass ratio to the 1 to the 2 to the 3. So this is next to leading order to what is currently known in cell force. So it would be good one day to have an independent check of this. But at the moment we can only check these other ones because these other ones are leading order in sorry, next to Schwarzschild in extreme mass ratio. So this has been checked. These ones we don't have anything to check. Okay, so maybe I can stop here. Yes, here I wanted to say something about how to tackle higher orders. At higher orders, in this approach of having the post-Newtonian approximation in the near zone of, expanding the integrals, you get a lot of proliferation, exponential proliferation of diagrams. But okay, what happens? Sorry, let me just be very brief here. Is that as you go to higher and higher orders, in computing the effective potential, most of the diagrams become factorizable. So basically, they're computable via algebraic manipulation from lower order diagrams. So we did this exercise to compute all of the factorizable 5pn diagrams from lower order diagram that we knew already. And you see, for instance, the G5 V square, which is a 5pn result, we already compute all of the factorizable, which are 2/3 of the total. And then at the same time, there was the results by the German group about the full 5pn. Of course, they also compute the non-factorizable that we didn't, but the factorizable were a subset of them, and then we could match, and they agreed. And okay, just to conclude, so PN approximation is really, really good because it makes, when you want to compute the effective potential, it really takes an intractable problem to something that you can treat via this double approximation near and far. This introduced some spurious divergence, which actually is not bad. Actually, it's a good thing because then it introduces a highly non-trivial check of the correctness of your computation. And the UV divergences, the real UV divergences that are related to the getting the black hole as point-like particles are completely understood in terms of counter terms that vanish on shell. And if they don't vanish on shell, that means that they are signaling the effect of tidal deformation, which we don't see at the moment up to 5pn. And then what are, if you want to go with this program at high order, then you have to face basically two problems. Diagram proliferation, but we think that we have this under control. Then the real problem is that at higher order, you really have to face new master integral. And that will be the bottleneck for anybody, PN or PM or whatever. Okay, I can stop here. Thank you.
Okay, thank you, Riccardo. Let's see if there are questions. You're a bit on your time, but there is still a few minutes for questions, if anybody has. Okay, I see Luke and Thibault. So I didn't see who was first, so let's start from Luke in alphabetical order.
Hi, thank you for the talk. Just in the end, when you show the 5pn tail effect, so they are decomposed with a quadruple tail, octuple tail, and so on. So in this calculation, you need the expression of the quadruple moment at 1pn order to be consistent. Yes. Mm-hmm. And my question is, do you derive the 1pn correction in the quadruple moment from your connection that you showed previously between the near zone and the far zone, which should be equivalent to the matching that people are using in standard post-Newtonian expansion? And have you checked independently using this procedure that you recover the same post-Newtonian correction in the quadruple moment?
Yeah, no, we didn't because, yeah, sorry, I thought you finished. Go ahead.
Oh, my question is, do you derive it consistently within the EFT using the connection between near zone and far zone that you showed in your first part of the presentation? or do you simply use the result from standard PN theory?
Okay, I answer now. Sorry to interrupt you. No, we do neither of the two. Basically, we just take the quadrupole as it is. This is the form we show in the paper. The quadrupole, whatever it is, it will enter the correction in this way, and then you plug in the formula for the quadrupole that you have. We didn't care about computing the actual correction of the quadrupole. I mean, this formula works basically at any PN order. Then you decide what PN order to stop by plugging in the appropriate form of the quadrupole. We didn't do it, but some other people did it up to 2 PN. There is the group from Carnegie Mellon, I think, no, Leibovich et al. They computed the 2 PN flux within EFT. So they really computed 2 PN correction to the quadrupole, 1 PN correction to the octupole, and so on. And I assume they have the same result as you, otherwise it would be.
Yes, they obtain the same result. Thank you.
Yes. So it's Thibault turn to ask a question.
Yes, just before posing my question, there is actually a problem, as you know, with the magnetic quadrupole, because you need to derive it in D dimension, not in 3 dimensions, and then there are many subtle issues. But it's not the question I want to ask. I want to be sure I understood. So what you were saying about the LQQ terms and the QQQ terms. So, so you're saying that the conservative effect of these terms is obtained, would not be correctly obtained by using the symmetric Green's function everywhere for LQQ, for instance, each part, because that would not give G retarded square and G advanced square, but G symmetric square. So for this thing, and then for the other one, the one on the right, QQQ, are you saying that a computation, like an amplitude computation using G Feynman cube, now would also not give the correct result? Just to understand.
Sorry, no, I don't agree with what you said. Probably I wasn't clear. Thank you for the question. So for this diagram in which we have, yes, 3 green functions, but only 2 of them are full green function. This one is 0 time momentum. You can use either the Feynman or the advanced retarded because of this relationship. This is, I mean, you can check it in 5 minutes.
Yes, but from this relation, I would conclude that one cannot use G symmetric square, because that would be GR plus GA square and not GR square plus GA square.
Ah, right. Yes, what you have to do the appropriate, which is, I mean, some overall possible orientation, all the possible physical orientation are retarded, or advanced, which is exactly what is written here. And this algebraically is exact apart from the imaginary part, which is the dissipative bonus. So this is the prescription that you have to use, either Feynman square or retarded plus advanced. For the case in which you have 2 full propagators. For the case in which you have 3 full propagators, so this is the right prescription, retarded, advanced with a negative momentum, which is retarded. Here again, you could write this as retarded advanced by changing the sign, of course. This is the right prescription. We tried to express this in terms of Feynman function. We didn't succeed. I mean, it's difficult to find, and we think it's not possible. But this gives you the right answer. If you put naively Feynman, for sure will not get the right answer.
Okay, but then I think that in your paper, when you cite the value of the 2-loop integral you need, you use a result from the literature, which is computed in the Euclidean after Wick rotation, which then uses Feynman cube, no?
But that's exactly what I say here, you see. The nice thing is that we don't need that integral. We just leave it indicated, whatever its value is. And the nice thing is that it cancels when you add all of the polarization. If you want the result from only one polarization, yes, you would need that integral, and we wouldn't know how to compute it. But you can just leave it indicated at x, and it just drops out, as it should, because we know this integral is fine. Actually, we know that the integral was fine well before computing it, and it drops out. But yes, you're right. If you want to compute the contribution from a individual polarization, which is divergent, we would need to know the 2-loop master integral with upper boundary condition, which, as far as I know, is not known.
And the fact that in your preprint and first published version, you got a result that then you change, is it linked to subtleties in the constellations, just to understand?
No. So we did a mistake. So we had an erratum. So this number is the number that you find on the archive and the number that you find in the erratum. If you find a paper published on PRD, you don't find this number. But we did a mistake that was the following. You see here you have to use, as I said, sorry, I forgot. You have to use, retarded advance. That means that the three the three momenta do not enter symmetrically the vertex. In the version of the paper was to treat symmetrically. Basically, we compute for one ordering and then multiply by 3. And this is wrong because the three momenta, they're not three. One is coming. One is use the advanced propagator and to the retarded. So basically, we overlooked it. We just assumed that we could multiply by 3 one orientation, which is not correct. So we used the right function, but we just did this silly mistake that we corrected. So if you look at the present version of the paper on the archive, it contains the right answer, and in the erratum, you find the explanation of the correction. Actually, on the archive, there are 3 versions. The second version corrected the typo with respect to the first version. The second version to the first version corrected the typo. The third version on the archive with respect to the second version corrected this thing that is explained in the erratum. Was I clear?
Yes, thank you.
Okay, I think we are way behind schedule, so let's have a coffee and let the organizer tell us when we have to reconvene.
I guess it's me who's the next chairman, so I would recommend 5 minutes to the hour, so that leaves 9 minutes for the break.
Okay, I'll see you later then. And thank you, Riccardo, again for the talk.
Thank you. See you.
Thibaut, since you are here, I think the dimensional thing about the magnetic quadrupole was we discussed that with Johannes and
sorry, I forgot to answer about that, but go ahead, Stefano, then I will add.
I mean, we're just having coffee.
It's not
now,
an issue anymore.
Because there was this epsilon, which I was considering D-dimension, but the epsilon which are introduced in the coupling are just placeholder for antisymmetric contraction of deltas. And in the end, they disappear from the result. So if this is what you mean.
No, I mean, okay.
Thibaut, can I add something?
Yes.
Yes. Before that, so there's no problem with the magnetic quadrupole. I mean, if you do the things correctly, as we did in the first version, the second version, and the third version, we didn't change the number. You get the number we present. There's no subtlety in the d equal to 3 limit, because the epsilon that you introduce is never there in the first place. You introduce 2 epsilons to reproduce the antisymmetry. But if you start with the general relativity prescription, which is antisymmetry without epsilon, you don't have any d's, and then you get the right finite piece from the right divergence. If you introduce the epsilon spuriously, because you want to antisymmetrize the epsilon, then you have to be careful to take track of the d's. But then, of course, they cancel as they should if you do things properly. So there is no ambiguity. You just have to do things properly. The thing is that when you write J as epsilon xt, and you write the Riemann, the magnetic part of the Riemann as epsilon r. Yeah, go ahead.
I understand what you are saying, but there is still the issue of having the magnetic quadrupole moment in d dimension because of the 1 over epsilon.
No, no, sorry, then I wasn't clear.
No, it's a
the fact that you write the epsilon.
Riccardo. Thibaut is mentioning some group theory, no?
Yes, there is, okay, but the value, yes, the value of the, like, you know, I mean, a long time ago, we computed the quadrupole moment in d dimensions, and you have explicit d factors. So if you don't have the formula for the magnetic quadrupole moment in d dimensions, your formula is maybe correct conceptually, but incomplete or not.
Well, probably you have to put the right Jij once you do the computation, but if you leave it as a placeholder.
Yes, yeah, I understand.
Yeah.
not
okay. Yes.
not a conceptual issue. I'm saying practically speaking, to get a number.
Yes, to get a number. Okay, I see.
No, what I mean is that Thibault, so we had a conversation with the German group about this, and not only we confirmed our result, they were convinced about it, and they check it because it affects the result at next to leading order in the symmetric mass ratio, so it's checkable with the extreme mass ratio computation, and according to what is written in the paper, is okay. And also from the conceptual thing is that you spuriously introduce an antisymmetric tensor to define J, but it was never there in the first place. And if you look,
I understand. I interpret positively what you are saying about the epsilon. I just wondered about the need to compute the value of the good Young tableau version of Jij, okay, without epsilon, with 3 indices, let us say, but in D dimensions.
That's true.
Can I
but
myself
you don't.
in the discussion?
Yes, please.
That Luc did recently, no, or what?
Yes, this is in preparation, but I showed just a slide in my presentation.
Yes,
so we defined exactly as Thibault says the current or magnetic multiple moments using irreducible decomposition of tensors in all the irreducible pieces. And so the generalization of the current moment for D dimension is more complicated. There are 2 objects actually, which have non-trivial symmetries described by Young tableaus. So the problem of defining the magnetic moment in D dimensions arises at 3pn order, because at 3pn order there will be a pole due to UV divergences. But I think a different problem is what you ask, Thibault, is that because the magnetic moment will be in front of a pole, you need to compute to order epsilon included.
Yes, that's.
And so already.
But you did that recently, no? You did that recently, or not?
Yes, this is not yet published.
It's not yet published. Okay.
No, it's in preparation. But then on the formula showed in Riccardo's slide, because of this epsilon, already there you have to compute it at order epsilon.
Yes,
epsilon, which is,
I'm
not sure that the argument with the double epsilons, which are just product of deltas, is correct, because in principle, in the full general, in the full theory in D dimensions, I mean that the full theory in D dimension, it's not obvious to me that it can be written by writing GR in 3 dimensions and cancelling all the epsilon and replacing all the epsilon by deltas, and that's the correct result in D dimensions. So,
no, sorry to interrupt. Sorry. I think we had a there for the next speaker. Is that okay? It's Carlos here. Carlos Lousto.
Hello.
Yeah, hello. Okay. Do you want to share your slides?
Yes, I'm really happy to.
Your sound is a bit weird, Henrik.
Oh.
Okay, now it's fixed.
It's better. It might be a bad connection. Let's see if I use my phone instead.
Are you going to chat, Stefano?
I was trying to, yes.
Because indeed we have to leave the audio. Yeah.
Okay.
This is a perfect discussion for Slack.
Exactly.
We need to get used to Slack. I'm not.
That's right.
Yes.
Well, we're hoping.
All right. So is my sound better now?
Yeah, you sound fine now. Thanks, Henrik.
Yeah. I think it's a bit unstable, but I'll try to manage.
Yeah, that's good. Thanks.
All right. Do you want to start sharing your screen or slides? All right, I guess we still have 1 more minute, but I will, just to let you know, I guess you have 40 minutes plus 5 minutes question, and I will give you a warning in 35 minutes. So that's 5 minutes before the questions.
Thank you. Can you hear me well?
Yeah, I can hear you. Great. So maybe we should start, because now she's 5 minutes to the hour, according to my clock. So I welcome you back for the last session of this workshop. And the next speaker is Carlos Lousto, and he will tell us about numerical relativity at the extreme. Please go ahead.
Well, thank you very much. I wanted to thank the organization of this wonderful conference for inviting me and having also many, well, all of the presentations are excellent. In particular, I want to recommend those interested in this subject, the presentations of Franz Pretorius on Monday and Harold Pfeiffer on Tuesday. They did a wonderful job telling the interesting things going on in numerical relativity. I'm humbled by the high bar they set up, and I will try to somewhat supplement those presentations. I like always to start with a picture of our center that has on top of this very long window this waveform that at the time was the longest published, with 100 cycles simulated, and it connects somewhat our lab with the computers, supercomputers, or computer clusters that we use for numerical simulations of binary black holes, with this folding mirror on the right hand side to this LIGO first generation from Hanford that we had in exhibit at the entrance of our center. Let me briefly mention what I would like to speak. Well, there is a lot of material to speak about. I won't be able to cover everything. Essentially, I'll make a brief review of the numerical relativity breakthroughs that allow us to simulate binary black holes and interesting processing dynamics effects due to spins that we can evaluate explicitly in order to cover some of the extreme simulations that are quite challenging. I will focus on the small mass ratio. There are, of course, large separations, long waveforms, high spins, high energy, 3 and n black holes. There is a lot of material that I won't be able to cover in this talk. I will then, if I have some time, I will move to the application of numerical simulations, and in particular computation of waveforms to extract parameter estimation from gravitational waves, namely LIGO, Virgo, and other gravitational wave detectors coming online. And I will skip much of the calls, and I don't have time for those. And then we'll try to give a brief summary about this. Well, since Helvi mentioned Doyle's Sherlock Holmes, I would like to mention actually the one that Doyle's inspired on, which is Edgar Allan Poe. That well, is the creator of the modern detective stories style, and yeah, I subscribe to the idea that we are always eager to find and investigate mysteries that we are interested in this case, binary black holes and gravitational waves. That was a nice quote from Helvi. Well, let me well start from the beginning. so for all the young people that have come to science with the binary black holes already solved, that was a very frustrating problem that took nearly 40 years to be solved. And many techniques have been developed in the meantime, but it was only till 2005 that we incredibly, in the second semester of 2005, in 4 months, from July to November, 3 solutions to the binary black hole problem have been presented. And this is what allow us until nowadays to extract information about these black hole collisions. And Harald made again a wonderful review of what is done with spectral methods. And I'm focused more on our method that involves moving punctures. They are completely different techniques, and I think it's fantastic that the field can cross-check and have independent techniques for solving Einstein equations. The 2 methods are they complement each other, and they do things completely different, from initial data to the numerical methods, evolution, the variables that we use, the formalism that we use to decompose Einstein equations are different, completely different. Gauge conditions are different. Singularity determinant difference, the size we avoid. And boundary conditions are different. Discretization methods are different. We use finite differences up to 8th order, and they use pseudo-spectral method. Measure refinement is different. So this is a table that we put together right after the first detection to stress these comparisons. And I was saying it is fantastic that when we compute the waveforms, they lie on top of each other with a matching 99.9%, as we put in the detection paper. So this allows us to say that we were really solving Einstein equations for the binary black holes. So one of the first results that I want to bring up here is that early, right after the breakthroughs, we decided to study what happens with the spins when they were aligned or counter-aligned to the orbital angular momentum, and compared to the non-spinning case. And yeah, we found that there is this strong coupling, spin-orbit coupling, that leads to quite different trajectories, even if you start from the same initial point. So this study in the amplitude of radiation was very different. So this study was interesting to show, for instance, that this spin orbit coupling produce a repulsive effect, that even if you started with a total momentum, angular momentum larger than the mass square, right? So we're going to violate, let's say, if they do merge them right away, the cosmic censorship. Well, this hang-up effect that keeps radiating angular momentum ensures that for the time you are ready to merge the 2 black holes, the total angular momentum is less than 1. So we found that the cosmic censorship was respected. Well, this was for aligned spins. So we did, the next thing we did in 2008 was to study a genetic processing system, unequal masses, spins pointing elsewhere, not aligned, counter-aligned. And the orbit looked like, yeah, processing. So it was interesting because of this computational challenge that Kitson had put in 2002. And he was saying, I bet these numerical relativists that gravitational waves will be detected from black hole collisions before their computations are sophisticated enough to simulate them. I expect to win, but he was hoping to lose because it was, the site continues, he was hoping to lose because numerical simulations were crucial, he says, interpreting the observed waves. And so I purposely designed these simulations early on and tried to conceive this bet because, yeah, we could do, at the time, 9 orbits were long. We studied conversions, we extracted modes, we compared to PN, the early part, everything worked very well. So the problem was essentially solved. I want to bring 2 interesting effects that we studied later, so in 2015. So one of them is that I was interested in, again, inspired by some discussions with Kitson on the fact that if during orbit, the spin of a single black hole could flip, right, from oriented to towards the orbital angular momentum, and then to flip to anti-align during the orbital motion. And so we studied this configuration. This is the configuration that I was showing you is on top of the window of our center. And it at the time was the longest one, so 20,000 M. And hopefully we can see this animation where we can see the spin, well, gravitational waves during the orbital motion, right? And the spin of the black hole that is initially oriented upwards. You will see the blue one, and you will see it starts pointing down, 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 down. And then, well, they are about to merge. And there they are, merge. And you have this big amplitude of radiation. And then you end up with a curved black hole in the very end. So that was made very quick because we are running out of time always. But of course, this is available. And we can show that this also happens for different mass ratios. The angle keeps shrinking. So this is an effect for more comparable mass ratios up to 1 to 4. And this could have interesting observational effects if the binary is accreting in super massive binary black hole system. After collision of 2 galaxies, you have mini disks that are accreting, and imagine that you have this spin of the black hole flipping from align to counter align. So it's like your cafe latte. You start swirling in one direction, and then you decide to change, right, direction. And you see this transition and turbulent effect that may have interesting observational counterparts. This needs to be simulated explicitly because it's very difficult to get an estimate analytically. So that's one of the areas where GR magnetohydrodynamics could be making interesting predictions for electromagnetic counterparts for gravitational waves. This flip-flop actually has a frequency, a characteristic frequency. If we allow this frequency to go imaginary, we get an instability of alignment, right? That we could again follow. This was first pointed out by Gerosa et al., and we have successfully modeled it with this. So we got a much better analytic expression for where this unstable region is in parameter space. Okay. The second effect I wanted to mention here is these beaconing binaries. And as we can have during orbital motion, flipping of the individual spin of the black holes, now what we could have is the flip of the L, the orbital angular momentum, under certain conditions. And this again happens for a smaller mass ratio. So it's complementary of the spin flip is for, let's say, equal masses to 1 to 4, and this beaconing is below 1 to 4. And we study for 1/7 and 1/15 evolutions. And the interesting idea is that they, this is a law of radiation, they start, well, in the orbital direction, positive and negative, with a maximum radiation of gravitational waves, but eventually, for an observer and a fixed point, what we will see is a modulation with the precessing frequency, essentially, or the beaconing frequency of the amplitude of the gravitational waves. And the two polarizations behave very differently. The two polarizations, gravitational waves, that normally for inspirals, you know, they track each other by 90 degrees. So the modulations in amplitude are very different for the two polarizations. So this is an interesting effect to track with measurements of detectors sensible to polarization. Yeah, this flower is very very artistic, but it was actually computed from the trajectory. So this is how the orbital plane flips from the original z direction. Okay, and so this is the power. It is having this modulation on top the orbital motion. That was again a very interesting effect with corresponding observational consequences, because again, before the steam flip was about how you steer around the mini disk, and here is the actually more the circumbinary disk that gets L pointing one way or the other. So this is another independent effect for electromagnetic counterparts follow-ups. Okay, so finally, let's go to simulations. The starting point is precisely what I was mentioning, this beaconing binary. We had to be able to track this 7-to-1 and 15-to-1 very well during all this motion. And we realized that we hit a very nice configuration of the refinement levels of the adaptive mesh refinement that we use. It was extremely efficient. So the idea was that if it worked for 15-to-1, what we wanted to do is to half the mass of the smaller black hole, so halving the mass ratio, and adding a refinement level at half the distance. And then kind of scaling down the mass of the black holes and adding refinement levels by a factor 2. And in this way, we would be able to keep track of this sequence of, okay, 15-to-1, 32-to-1, 64-to-1, and up to 128-to-1. That is the new record of a small mass ratio. We had made a proof of principle some years ago of 100-to-1 for 2 orbits. What I'm showing you is a presentation of the curvature of the large and small black hole magnified during the 128-to-1 13 orbits prior to merger that we succeed in evolving. So I hope you can see. You will have, I always say that those simulations is a test for your good sight. Well, don't complain if it is very long, because it took 6 months to evolve in a supercomputer. Okay, and finally hits and gets. Okay, so we were able to extract from these sequences of smaller and smaller mass ratios, well, the final black hole mass, merge, and spin, of course, recoil velocity, the waveforms peak luminosity, peak frequency, and peak amplitude. And also we made the consistency check, which is between the radiated energy carried by the gravitational waves and the mass, the final mass of the black hole, or the final spin of the black hole, compute from the horizon and take the difference from the initial total ADM mass or ADM spin. And we find consistencies. You see differences are 10 to minus 5 in the mass and 10 to minus 3 in the spin. So we were happy to find this consistency. So number of orbits of merger were 10 and 13. We started from some separations and we didn't know how long it would take to merge. But we can, after the fact, we can put them together and see the merger time as a function of the evolution time. And yeah, so we found this intermediate dependence with the mass ratio, which is in part the plunge itself that is independent of the mass, and the orbital part, which is depending with eta to the minus 1 over q essentially. So everything looks good. The waveforms are like this, just to compare length and amplitudes for the 2 modes. And so we came back and did different resolutions for 15:1 to check conversions of the results. And we find very good conversions to these bulk quantities, energy, angular momentum, radiativity, recoil velocity, all these 6 parameters that we measured, 3 at the peak and 3 at the remnant, and also the amplitude and the phase of the waveforms themselves converge nicely, nearly fourth order. Now, recently we have also extended these conversions to the 32:1 mass ratios. This is just a zoom in of the last part of the simulation to see how this impacts the curvature of the curved black hole. Just the detail of the bang of the small black hole and the curved black hole. So one further analysis we did was the fact that we can model if I have time, I will tell you in more generality, but we can model in a kind of S-matrix approach what are the initial parameters of the binary black holes, individual masses or mass ratio, individual spins, and then what is the final remnant mass and spins, and recoil velocity, peak amplitude, peak luminosity, and peak frequency, right? And so in the case of non-spinning black holes, as we have here, we have 3 parameters to fit for each of these quantities. What I'm doing here is comparing a previous analysis that we did for equal, this is mass ratio, equal masses, then to essentially 10:1 mass ratio. And we have found this curve that nicely fit these 6 quantities. So this was a previous work to our simulations of a smaller mass ratio. So there is no fit here to the new simulations with our level with the stars. And we see that they go, the extrapolation of our previous work, they go through the 4 points, 15 to 1, 32 to 1, 64 to 1, and 128 to 1. All of them go through, well, the one that has some more difference is the peak frequency, because it doesn't scale with eta. And this gives us an estimate of what kind of errors we are making in these simulations. So the estimated errors are around 2% from these quantities, these remnant quantities. And we find convergence and horizon versus radiation consistency. So we know that we are doing things that which makes sense, right? So of course, this was the first case, the exploratory case. We can add a spin to the large black hole. We can add a spin to the smaller black hole. That's going to be the strategy for creating more accurate waveforms for third generation gravitational wave detectors and eventually LISA. But of course, we are also interested in the performance, not only the accuracy, but also efficiency of the code. And we are exploring different gauges that can improve the accuracy and can make us gain speed as well for a given accuracy. So we are exploring initial labs and shift choices and an evolution parameter for the shift that seems to be giving us very nice results. I will go through now applications, different, if you want, set of applications. Those that I spoke so far were exploring different properties of the simulations, right? The spin effects that have no Newtonian equivalent, and these small mass ratios. And now I'm going to go to the application of these simulations to estimate parameters in gravitational wave detectors. So is this essentially the use of catalogs, gravitational wave catalogs, in parameter estimation? As I was saying, one of the things is to consider these in-out S matrix that connects the spiral or orbital parameters of intrinsic parameters of the binary and the final black hole properties. And so in the latest release of our catalog, we have 477 aligned spin simulations covering mass ratios up to 5 to 1, and it spins 0.95 systematically. There are some 0.99 and 0.97, but systematically up to 0.95 spins. And we use this, the three colors correspond to the three releases of the catalog, and we use this to model the formulas. Now, I have shown you for the previous cases, a non-spinning case. For this spin-aligned case, you have, instead of 319 fitting coefficients. You can model them to, because we go to up to fourth order in the mass ratio spins, and well, with the spin 1 and spin 2, but we collect them with in terms of these different variables that make a more robust fitting of these parameters. And these are the formulas for the final remnant mass, final spin, recoil velocity of the remnant, and peak luminosity, peak amplitude, and peak frequency. You get some quality measurements of the fits. The fits are really very good and working the whole range. One of the things that I wanted to mention is in one of the first slides, we studied this hang-up effect when the spins are aligned or counter-aligned with the orbital angular momentum. We see this delay or prompt merger. And the first work where we studied this effect was with equal masses, and now we extended this to unequal masses. In doing so, we realized that an interesting effective spin to describe the merger of the binary black holes is this hang-up parameter, which is slightly different than the one that you derive from as effective parameters from Post-Newtonian that is more adapted to the inspiral region. But in practice, they are close, but not so identical. So I said I won't have time to speak about recoils. And well, let's speak now about the specific events. So in addition to the 477 non-processing, we have 300 processing binaries. This is where the spins are pointing in the two sphere. And what we have done is to compute matching of each of these waveforms to specific events and do color maps, heat maps for spin 1, spin 2 for each mass ratio in the line case to detect where is the hottest region and what are the parameters we can associate to these each of these events to give a 90% confidence limits and so on. These are intrinsic parameters. This is the difference of this first event as seen with the standard chi-effective or Shu spin parameter that we put forward. If you look instead to the processing binaries, at the time this was done with the second release, which had 200 simulations instead of 300 simulations we have nowadays. We find that the hottest direction is for the spin in the orbital plane and mass ratios, comparable mass ratios. You can do these heat maps also for the remnant properties and get all the properties of the final black hole with estimates of their errors. We can also determine the extrinsic parameters of these events where they are pointing in the skies, what is their distance, inclination of the binary, and of course compare the top full numerical simulations to the reconstructed waveforms from the data. We did this also for the first event in the O2 observation of LIGO. And recently what we decided to do is to prove that we can run over all events of O1, O2, the binary black holes events. So there are 10 events in the standard LIGO catalog. But we also extended to 3 events that were reported by later by a group in Princeton. And here is a result of reprocessing the first event. And what we found is that the dashed line is the 90% confidence of LIGO. This is what we are getting now with our simulations. So it's, I don't know, 1/3 the surface, so it's more accurate. When we try to mimic the same, and this is using our priors, we try to mimic the same priors as LIGO, we get this dotted curve, which is still an improvement on LIGO. And this was with the line 477 line cases. You can do the same analysis independently with the 300 processing simulations, and you get something consistent for the mass ratio. Here, the total spin essentially 0, so this is equivalent for the processing case that is in the orbital plane. And we will see more detail here in this table for the 10 O1 or 2 events plus the 3 events of Princeton. We are able to provide well, mass ratios, spin 1, spin 2, total mass, also this comparison of effective spins, and this is for the 477 aligned cases. The 300 processing can be used independently to determine also mass ratios and also total masses, which are compatible with the previous analysis, and also a direction of where the spin was located or pointing initially for all 10 plus 3 events.
Excuse me. You have 5 minutes left plus questions.
Thank you very much. So we can also determine not only the intrinsic but the extrinsic parameters. So essentially, what distance are each of the events, what is the right ascension and declination, what is the orbital inclination and phase at periastron, so at merger time, and we provide also the 90% confidence intervals. That's also true for the final remnant parameters. We can provide the final mass, spin, recall velocity, and peak luminosity, peak frequency, and amplitude for the 10 events plus the 3 of Princeton with plus minus. By the way, our determination of or estimation of parameters for the 3 Princeton events agree very well with those provided in the original Princeton paper. So that's I think it was an interesting result. Okay, so we always get questions about the accuracy of the waveforms and if they are good enough and so on. So the answer is yes, they are very good for LIGO. When we speak of LISA, it's another discussion, but for LIGO, Virgo, Cagra, future detections in this generation, we are good enough. Here is a few selected cases that we had 3 near the peak likelihood. We had 3 resolutions, low, medium, and high, and the likelihood, as you see, didn't change. Here we found a small change, and so we are able to extrapolate to infinite resolution. What would be the difference between even the lowest and the infinite resolution? We get about 2% difference in the likelihood. So this is very well covered by 90% confidence limit, even 95% confidence limit. So not big sensitivity of this likelihood measurement or matching of events versus numerical relativity resolution. Another test we performed was, okay, what happens if you try to detect parameters of the signal, right? So essentially it's a null test to control our method. We run our method and we get, well, essentially the priors, if we have some bias on the priors, and we get flat for the spin to the more massive black hole, flat for the spin 1, flat for the mass ratio, and the total mass of the black holes with some particular choice around 50 solar masses, because the length, particular length we have chosen for our simulation. There is one more event that we were interested in, which is already in O3, and is this event that LIGO reported, and it wasn't very consistent. And what we did, we allow simulations with eccentricity, and we found the likelihood of some high eccentricity, initial high eccentricity, to be higher than assuming 0 eccentricity. So it is interesting that for this event, there could be some eccentricity effect that cannot be discarded a priori. And we also point out that if we assume the electromagnetic counterpart that was assigned to this event, while LIGO assigns a certain distance of around 6 gigaparsec, we found rather about 2 gigaparsec because of the centricity effect, right? So if it is more of a plunge, radiate less, so it has to be closer to us. And with this estimated distance, the Hubble constant fits very well with other measurements of Planck and shows instead, LIGO is in the 20s for the Hubble constant. So this seems to be an interesting result. Well, there is still a lot of interesting challenges up there, as Franz Pretorius and Harald Pfeiffer mentioned. There are high spins, black holes, there are smaller mass ratios, neutron stars, combinations, and the good thing is that we can always get more simulations and improve our catalog coverage of the parameter space and keep extracting those estimated parameters. As we mentioned, third generation detectors are interesting challenge in the LISA, but we do have time for that. So I think I will stop and thank everybody here. And in case we have some questions, I will be happy to answer.
Thank you. Thank you for a very nice talk. Do we have any questions for Carlos? Oh yeah, I see a question by Jan. So please go ahead, Jan.
Yeah, thanks for a very nice talk, Carlos. I have a not directly related question, but are there also simulations of just scatterings? I mean, not in spirals, but scatterings of two black holes, because that's the situation that, you know, from a perturbative side is studied very intensively these days.
Thank you for the question. What we are about to, I need to finish classes, give my final test and write a paper for which we have simulations of high energy collisions of black holes. And so the interesting thing for us is well, most of this, we're interested in the verge between merger and scattering. So that's our study. And we do have, so Harald, I think, mentioned correctly that the standard initial data has limitations, not only in the spin, but what is the gamma factor you can give to the black holes. But we have a new, relatively new set of, or different set of initial data that allows for not only high spin, but much higher energy collisions. And yeah, we will provide energy, angular momentum, and linear momentum radiated for those collisions. We should have this written in a month or so. But scattering per se, I haven't studied. I think Harald has nice results coming up soon.
All right, I don't see any further questions. So unless there's any questions, maybe we should thank the speaker then. So thanks for a very nice talk.
Thank you.
And if there's more questions, you can ask offline on Slack or etc. All right, so the next speaker is Ira. So is Ira here? Can he share his screen? All right. So I guess we'll start shortly, but let me just tell you that you have 40 minutes, and 40 minutes plus question, and I will give you a warning 5 minutes before the question starts.
Okay.
All right. So the next and the last speaker of the conference is Ira Rothstein, and it will tell us about black hole response theory. So please go ahead.
Thank you. Okay. So I want to tell you about some work mainly done in collaboration with Walter, and the most recent work also with Jingpin Li, who's a student of Walter, who's going to be starting a postdoc at CMU in the fall. So the ultimate goal relevant for this conference is to understand how much information we can get from the gravity wave signals about the internal structure. Well, I should say this is part of the goal, aside from obviously GR questions, the internal structure of the objects that are inspiraling. So I'm going to talk about a general methodology for attacking this problem and some of the applications that we've done so far. So basically the way we think about it is if we blow up this square here, then we're really interested in how some finite size object responds to external perturbations. And of course, how do we measure? Sorry. How do we measure the internal dynamics of a system simply by looking at scattering off of it, right? So the response function, I can't get rid of this. There we go. The response function encapsulates all the interesting physics that we're interested in, right? So if I do a condensed matter experimentalist learns about the internal structure of an object and its dynamics by scattering off of it. And in our case, what we want to learn about the internal objects are the love numbers, the tidal responses, of the absorptive effects. And in the case of black holes, part of the response is also encapsulated, or the response also encapsulates the Hawking radiation. So we'd like to try to extract as much information as we can about these characteristics from the response function. So to leading order, we can consider linear response theory. Everything I say here is extrapolatable to higher orders in a systematic fashion, but I'm just going to discuss the linear response, and if there's time and interest, I can talk about nonlinearities. So when we probe any system in this way, the response is encapsulated in correlation functions of operators. Usually those operators correspond to some conserved currents in the theory. And all the 2-point functions, all the information about the 2-point functions can be encapsulated in 2 Whiteman functions defined in the top row, and the Feynman or time-ordered and anti-time-ordered Dyson Green's function. And there are relations between these functions that we'll take advantage of. But in principle, if you knew, if you have all this information, then at least at linearized order, you have everything you need to know about the system. Now, which one of these 2-point functions you're interested in depends upon the context of the calculation, or I should say depends upon, sorry, it won't let me drag. All right, let me, I'm going to go back to my, my laptop because I'm having too much problems with my iPad. Okay, so as I said, which correlator we're interested in will depend on what we're interested in observing. So the first step, we're going to simplify the problem by considering only long wavelength probes. This is clearly what we want to do if we're interested in including the motion of the system itself. In other words, we want to keep the translational zero modes and perhaps rotational zero modes, so the position, something like center of mass. So we're going to consider the long wavelength approximation so that those zero modes are encapsulated by some collective coordinates which describe the spin and the position. So in the full theory, which is what I'm going to call the finite size manifest state representation, the metric couples to the stress energy tensor. Assuming the stress energy tensor has some compact support, then we can tailor expand around that center of support. And in so doing, localize everything to a world line, which here I've taken the metric to be at 0. And so the integral over x then just defines some moments that, that couple to derivatives of the metric. And if you do this in a diffeomorphism invariant way, of course, you get back starting with the quadrupole, if you, and then higher multiples, so forth and so on. And those Qs are eventually going to become our dynamical objects. They're not just constant coefficients. And moreover, we're going to treat them quantum mechanically. So those Qs are operators on the world line in some Hilbert space, which characterizes the system under study. Now, one of the first assumptions we make when we do linear response theory in general is that there are no long time tails, which is to say that in Fourier space, the correlation functions, both the Whiteman and the time-ordered, anti-time ordered, can be expanded around zero frequency. Physically, we can understand this because here I've drawn what would happen if you had a binary which they didn't have a long time, which had a long time tail. So at some early time t, these particles interact, and as they're in the orbit, one of them starts to stretch, and then as time goes on, it continues to stretch indefinitely. Then clearly linear response theory would fail. So the basic assumption linear response theory is that the time scale for deformation is short compared to the dynamical timescales that you're interested in. So it's an automatic, it deforms into whatever donut potato shape it's going to take, and then it stays like that until some hard scale is involved, perhaps. Okay, so now we have we've reduced the problem to calculating correlation functions on a world line. So it's a one-dimensional field theory, but we don't know what those correlation functions are. So we have to somehow match to the full theory in order to extract those correlation functions and then use them in subsequent calculations. So here in this diagram, you can see the full theories on the left, and then the response is encapsulated by those two. So the purple lines there is like the response of the system. And the important thing to understand is that the physics can be quite distinct. In other words, when I scatter light off of a condensed matter system, I do ARPUS or something, then I'm scattering on-shell radiation. And within the context of this orbit, I am working off-shell because the momentum exchange there in the potential is in off-shell mode. So sort of the power of the effective field theory, which all basically is an assumption of locality, lies in the fact that you can extrapolate, you can calculate, you can match on-shell and work off-shell. So you're not just replacing redundancies. In other words, it's not just, you're not just replacing A with A, but you're taking A and using it in a different context to gather information. Okay, so how do we match the correlation functions? Well, here I'm going to be talking about black holes, but you could do the same thing for neutron stars, or whatever you're interested in for potato. So we can use the results for, say, the absorption of one graviton on a black hole. Here we use the results of Bekenstein and Mizels from the 1970s, who told us what that probability is. In fact, they did N to M. They did much more general, and we actually utilize that. Those higher, you can use those higher quanta absorptive calculations to calculate higher order correlators beyond the 2-point function. But the 1-point function, or the absorption, this is proportional to the square of an amplitude. That's what you see on the right. And when you square the amplitude, it yields the Whiteman function. So the 1 to 0 probability can be written as the electric and magnetic Whiteman functions. So that is QE, QE, and QB, QB. So we can then use the result of Bekenstein and Mizels to extract those Whiteman functions. And here, this is what the result looks like. So now we're doing a leading order expansion in omega RS, because we're assuming we're wavelengths long compared to the size of the object. So now what's sort of interesting about this result is that this looks purely classical. So if I look at the top line, you can see that's the 0 to 1 probability, which is Hawking radiation. And we see that, so the Hawking radiation is controlled by A plus of minus omega, which is the same thing as A minus of omega. And absorption is controlled by A plus of plus omega. But in this limit, they're actually equal to each other. So it seems like absorption and Hawking emission scale in the same way, which seems, at first, that seems counterintuitive, because clearly absorption can happen classically, but Hawking radiation is a quantum mechanical effect. So that seems to be a little bit counterintuitive. However, as is well known, if you look at Hawking's formula for the number distribution, h bar omega over kt is independent of h bar. So that actually doesn't have any h bars. So it's not terribly surprising that that you find that the A plus and A minus scale in the same way. So this might, in fact, get you excited about the possibility of seeing Hawking radiation effects in gravitational wave experiments. And there, in fact, there have been multiple papers about this, but it's rather simple to see that that's not possible. And the reason is because when you calculate the equations of motion in the two-body problem, as we know, it's going to be a function of the retarded propagator, not of the Whiteman axioms, Whiteman functions. And if you look at the retarded propagator in a general density matrix, so if we allow, say, for the Hartle-Hawking vacuum or for the Unruh vacuum or Boolware, then at leading order, that commutator is just a C number, and then the trace becomes independent of rho. So the retarded propagator can't know anything about the fact that you're in a density state, a finite temperature state. It's independent of the choice of those vacua. So if there is a claim that you can see Hawking radiation, then it has to violate some of the fundamental assumptions of quantum mechanics. So I don't quite understand those claims. So now, as I said before, there are relationships between the various two-point functions, and the simple dispersion relation between the retarded propagator and the Whiteman functions. And so I told you the Whiteman functions were not suppressed by h bar, and they have Hawking radiation in them. So how can it be that GR is independent of the Hawking radiation? And the answer is that if you calculate the difference between A plus and A minus, then all the effects of Hawking radiation cancel. And so, in fact, we're curious how this works. So we looked in the Unruh vacuum, And so here you can see the result for A plus in the unroot vacuum, and this is also valid for A minus. Yeah.
¿Es mucho? ¿Quieres ayuda?
Oh, sorry.
Okay.
So you can this A plus is valid also for if you take A plus and minus, that's A minus. So the difference between A plus and A minus we can calculate directly. Beta H is the Hawking temperature, and you can see that in the difference the Hawking temperature cancels. So this explicit calculation, the unroot vacuum, shows indeed that the hopes of seeing Hawking radiation may be dashed. Of course, if you go to higher orders, then the commutator will no longer be a C number, and then but then those will be suppressed by the Planck mass, usually as in quantum gravity. But we could ask, well, let's look at some other observables which are sensitive to the Whiteman function. So the simplest one would be, say, scattering, quantum mechanical scattering. So here we're looking at the scattering of a massive scalar off a black hole. And we're going to assume that the mass of the scalar is too large to have, for the final states to be a consequence of Hawking radiation. And we can calculate the scattering amplitude, and the scattering amplitude is proportional to the Whiteman function. So this tree level diagram will be sensitive to Hawking radiation. And the interesting thing is that this Hawking radiation is off shell. The other important thing to note is that this is an inherently inelastic process. So we're summing overall final states X of the black hole. And there is a finite energy transfer as a consequence of that. So using the effective theory, we can actually calculate this cross-section. So if you look at scattering of a black hole, of a massive scalar off a black hole, then here's the amplitude squared. And you can calculate the cross-section just by putting in the right flux factors. And the interesting thing about that is that this scattering cross-section scales in the same way as the usual one-loop quantum gravity corrections to scattering. So this is a correction to a leading order quantum gravity correction that, as far as I'm aware, had not previously been noticed. And it comes from a tree level diagram. Okay, another application, this is actually, we never published this, but it's kind of an interesting application, is you can talk about black hole soft theorems. So we know that there are soft theorems which tell you how to generate a scattering amplitude given a hard scattering. If you just want to add one soft quanta, you just hit it with a soft factor, a canonical soft factor. And you can do the same thing now with black holes. So if you scatter black holes and ask, what is the effect of the acceleration of the hole due to the scattering process, then there's going to be some interference in the Hawking radiation. And so it's an interesting question to ask, how does the scattering affect what you see at infinity? And you'll see these interference effects, which will distinguish it from just the vanilla Hawking radiation. And what's relatively easy to prove is that you can take any square of a scattering amplitude and generate the one graviton emission just by hitting it with a simple soft factor, but it works at the level of the amplitude squared and not at the level of the amplitude as it does in normal soft theorems. And that was just an aside. Okay, so now to more phenomenological applications. Let me show you how we use our formalism to calculate absorptive and finite size effects. And when I say, I'll tell you exactly what we can and cannot calculate. And this builds upon earlier work by Eric Poisson and Raphael and Solomon Enlich and Riccardo Penco in generalizing what they did in various different ways, depending on which paper we're looking at. And I should also say, I just recently, meaning right before this talk, found out that there was a paper in 2001 by Helvi, whose results are very similar. I haven't checked yet how they differ or if they differ from Poisson. So I apologize for not including that reference. So how do we include these response functions into the world line theory and calculate, say, absorptive potentials, or even include the effect of love numbers. Okay, so I'm going to start with the Polyakov form of the point particle action, and then I'm going to add to it some degrees of freedom that live on the world line. We'll call those degrees of freedom X, and we're completely agnostic about what they are. So at this point, it doesn't have to be a black hole; it could be a neutron star. And then, as before, we couple the electric and magnetic part of the Weil tensors to some operators on the world line, which depends on those degrees of freedom. And then we want to calculate the equations of motion. So to do so, we should use the in formalism. So it's the usual doubling of variables, which I've written down. And gamma here is the ineffective action. And by varying it, minimizing it, that yields the equations of motion. So here in the action, I should say we've introduced E. Little e is the Vierbein, and it generates a constraint. But now the constraint equation is p squared equals m squared plus the contribution of the internal dynamic. So the mass will shift depending on the expectation value of these operators in the state of interest. And then we could vary the action to get geodesic deviation. So if we vary with respect to x, then we get the usual geodesic equation. And the right-hand side is the expectation value of those operators and include all the dissipative effects. And now what we would like to do is to extract Q. So Q will be basically the induced moment on one particle due to the field of the other, and that's what you see in the second line. So G retarded gives that's the leading order linear response theory. The expectation value of Q will be determined by G, and E there will be the field generated by the partner. Okay. So now if we want to relate the Whiteman functions, which we've already extracted, to this G retarded, then we can use this the dispersion relation. So that that plus should be in the subscript. I apologize for the typo. And now if I decompose it into real and imaginary parts, you can see that the real part will still involve an integral over all frequencies, and the imaginary part is just local in omega space. So the imaginary part, of course, is the dissipative piece, and the real part is the conservative piece. And we don't know how to calculate the real part from this calculation because there's an integral over omega, and the effective theory is only valid for omega less than Rs. So that the real part contains all the short distance local information, including, for instance, the love number. So in order to extract the love number, this calculation, via scattering, will not be sensitive to it. There's always another way of saying that is that there's a local counter term for the love number. As we know, E squared can sit on the world line and is completely local short distance quantity. Okay, but if we use our results, we can get the imaginary parts, and the imaginary parts will tell us how the expectation value of Q. You could see that it's got one time derivative on the external field. It's time reversal violating, so that is the dissipative piece. And then we can calculate the mass loss, as you can see in the bottom line, just from knowing the change in P mu and the equations of motion. And this gives us the mass loss, and this is what Eric had back in 2004, and possibly also Alvi. I have not checked that paper. Okay, so now let's look at this. So this was all, let's say, in a background, arbitrary EB background. Let's look in the two-body system. So in the two-body system, we have a leading order exchange of a potential, and the Q1 here is the induced moment due to the original potential exchange on one of the bodies. And so we can effectively integrate out that graviton and generate some effective interaction, as I've done there on the first line. Okay, so now what can we use this for? Well, one possibility is to calculate in the PM approximation the scattering angle. This has been used to calculate potentials for the conservative piece. How to apply this to the since this is non-conservative I don't have the answer to. Perhaps someone in the audience does. But we decided to calculate the scattering angle in the PM approximation. So you can calculate just by treating the one Q interaction as a perturbation, a deflection of the momentum, and that leads to the bottom line, which gives you the scattering angle as a function of the momentum in the center of mass energy. Okay, so now let's go to the PN approximation. So in the PN approximation, again, we can integrate out the graviton leading to this effective interaction on the top line. And then by varying the action, we can get the force law. So I should say, so one thing that we've generalized here is that we have the time-dependent equations of motion, whereas in those previous results of Helvi and Poisson, they had, and also Raphael, they had only the average, orbit average quantities, which is phenomenologically probably irrelevant. So here are the equations of motion, and then from those you can calculate the energy loss for the system. Okay, now in the case of spin, I should say so. This effect is a 6.5, so it's not terribly pressing matter. The spin, of course, starts at 2.5, so phenomenologically is of more relevance. So for the spinning case, the methodology is the same. It just gets a little bit more complicated due to proliferation of, as you'll see, form factors. So so here, so to do the spin, you introduce a tetrad, a little e, a mu, for relates the orthogonal to the frame to the global frame. And we introduce some covariant spin supplementarity condition. So at this point, I haven't said anything about dissipation. We'll talk about that in a second. M here now has to become some function of P and S. So for a black hole, we know this gives you the Reggie trajectory, and for black hole, we know that for other objects we don't. So we have to leave that as some arbitrary function of those couplings, which is kind of interesting because at higher order, when you vary with respect to S, that could lead to interesting effects. Although my guess is they will all be small. Nonetheless, going to higher order would be very interesting. So now, as before, we're going to add some x degrees of freedom to the world line. And now P and S become functions of x. So now the canonical variables P and S are no longer considered canonical variables, which would seem to be a problem for figuring out what the equations of motion are. But I'll explain how we get around that problem in a second. So now let's see how we get the equations of motion. So varying with respect to x isn't the problem. And we generate the usual Matheson-Papapetra equations appended by the terms on the right, which are the dissipative terms. And varying with respect to the tetrad, we get the spin equations of motion the same way. So as I said, we can't vary with respect to P and S because they're not considered canonical variables, but we can still get the relation, say, between x dot and P by imposing the constancy of the spin supplementarity condition. And that leads to these results for the mass loss and the spin decay for arbitrary backgrounds. So as before, now we can match the Whiteman functions. And this turns out to be a little bit more of a, so we have to extract these Qs. We can still use the results of Bekenstein and Maisel, but they, as they gave results for spinning holes as well. So this becomes a little bit more of a technical challenge because there are 5 form factors. If you look at the QQ correlation function, you can show that they can be parameterized by a choice of generators in SO3, and there are only 5 independent ones because of 2L+1 for the representation that we're looking at. So that tells you that there are 5 form factors, which I've labeled here A+ sub j. And we can extract the result from Bekenstein for absorption of one graviton, which I've shown here, and then relate it to these expectation values, these form factors on the bottom line. Now, as I've said, we can't say anything about the real part. We can't relate the Whiteman functions to the real part because there's a short distance contribution, and those short distance contributions correspond to the love numbers. And so we're assuming the results of this paper in 2000, this paper by Chia, who calculated those love numbers in the spinning case and found them to be 0. Okay, so following all the same line of reasoning as we did for the non-spinning case, you can calculate the equations of motion by varying the in effective action and calculate the force law. And here's the instantaneous force law as a function of spin. Chi is the spin normalized to GM. So chi here, this is for arbitrarily large spin, but there's no assumptions about the spin. It could be maximally rotating if that be wished. And then a similar result for the spin change. Now, what's really interesting is that next to leading order, even for the average result, was calculated by Poisson and Eunice a few years back. And there seems to be a discrepancy between their result. They have found a discrepancy between their result and the expansion of the probe limit. In particular, some of the constants don't seem to agree. So that's the next calculation we're going to do to try to see if we can resolve this issue. But I should say that I think that there are many other applications of this formalism to both formal and phenomenological questions that we hope to explore. So thank you.
Thank you for a very nice talk and being well on time. So we have plenty of time for questions then. So please go ahead. I see a question from Carla.
Yeah, thanks a lot for the very nice talk. I wanted to go back to your comments about soft theorems, or rather soft theorems for squares, right, of amplitudes. So usually these are associated to the presence of some non-trivial asymptotic symmetries, right? At least at the level of standard amplitude soft theorems, right? So I was wondering here if you have any comments on that, especially since, as far as I understand, people have looked at analogs of super translation imprints on the asymptotic that are left by the asymptotic states on the Hawking spectrum, but eventually came up with negative answers.
So I can't give you a direct answer to that because I don't think of it in terms of the soft theorems as being a consequence of asymptotic symmetries. I think of the soft theorems really as being a consequence of local Lorentz invariance. So I don't think I'm going to be able to answer that question. I think the crucial, the simplistic way of seeing a soft theorem in general is that if when you have soft radiation, the propagator will iconalize, and so that naturally leads to a factorization, right? So as long as you only have soft radiation, then you're always going to get an iconal propagator, the 1 over b dot k.
You mean? Yeah.
Yeah. So I mean, so I should say, I mean, factorization is really, I think, I would say it's even independent of any gauge invariance, in the sense that factorization is really the statement that, you know, the long distance physics separates from the short distance physics. So that's really a consequence of locality. So you know, the fact that this also factorizes, I think anything would factorize if I had some sort of soft emission. So as long as the emission is soft, the fact that it factorizes doesn't really surprise me. So, you know, I know the arguments about soft theorems as functions of asymptotic symmetries, but I was never quite sure. It seemed to me like it's certainly sufficient, but it's not clear to me that it's necessary.
I see. Thanks.
Yeah.
Any more questions for Ira?
Eric?
Yep. Please go
I
ahead.
cannot raise my hand. So I have one question and then I have an announcement, but that I can make after all the questions are asked. So now I was a little bit intrigued by your comment about the Hawking radiation, you know, having no H bar in it if you express everything in terms of frequency, I guess, and the black hole size. And I'm a little bit puzzled because, okay, we have done some calculation of Bremsstrahlung in a collision in which you don't form black holes. And there we do find that the typical frequency of the emitted quanta is indeed of the order of, you know, 1 over the gravitational radius of the collision. So in that case, you know, the phenomenon is there. If I understood correctly, what you say is that in the actual black hole case, in spite of the absence of an H bar, the problem is the process doesn't happen, right? Classically. Did I understand correctly what you were saying?
I have a question about your first statement, but let me answer the last part. Yeah, so what happens is that all the effects related to, you know, if you express the Hawking radiation, if you parameterize it by beta H, then they all cancel. In other words, if you calculate the force between two black holes and ask, well, does the Hawking radiation contribute to that force? Yeah. The answer is no, unless you include bulk graviton loops. In other words, because the force law only depends on the retarded propagators, right? And the retarded propagators, the difference between the Whiteman functions. And so that the difference in the two, while each Whiteman function depends on the Hawking temperature, the difference of the two does not.
Does not. So you really have to go to a quantum.
You have to go, yeah. You have to include some loops to see it. So now, regarding your question, I'm a little bit, I'm not exactly sure. So you're saying are you looking at high energy scattering, and then you're looking at graviton radiation?
Yes, graviton radiation, and we do find that that the typical scale of the frequency of the emitted gravitons is related to the, you know, to the gravitational radius, if you want to, g times square root of s. This is where the spectrum peaks or has a knee and then decreases in energy. So in that process, even the Bremsstrahlung tends to concentrate on the Hawking scale.
Well, wait, there's no infrared divergence in the limit where it goes to 0?
In the limit what? When?
Where the energy of the graviton vanishes?
No, we are looking at the energy spectrum, and no, there is a perfectly finite zero frequency limit. It is well known. Now the spectrum dE over d omega has a zero frequency limit. Then it's almost constant for a while, and then it starts to drop exactly around the Hawking, the omega corresponding to the Hawking temperature. This is what we found. I mean, of course, the number of gravitons diverges. You're right, but not the energy, because there is an extra h bar omega.
Right, right. So wait.
So in that case, the process happens classically, and there is no problem. But I guess when the impact parameter is sufficiently small that you do form a black hole, then somehow that radiation shouldn't come out classically.
Oh, I see what you're saying. Okay, so at this point, the impact parameter is larger than the Schwarzschild radius.
It's larger than the Schwarzschild radius, so you don't form black holes, but you need quite a lot of gravitons, and the typical energy spectrum, has this cutoff at 1/r.
But isn't that what you would I mean, what other scale could be there?
Yeah. I mean, it could be 1/b. Let's say 1 over the impact parameter, which is a small.
Oh, I'm sorry. I'm sorry. R here is the radius of.
Yeah. G times square root of s.
Oh, I see.
The center. I mean, suppose we are in the center of mass.
Right.
Is that? Yeah.
That's yeah. So in that case, I mean, because there's no horizon. I mean, the vacuum. There's no ambiguity in what you choose for the vacuum, right? So.
Right. No, the calculation there is quite straightforward, but okay,
yeah, but it's interesting that it's interesting that it doesn't go like B.
Yeah. It keeps going, and I mean, it has still a logarithmic decrease at omega larger than 1/b, but it really has a knee and starts to fall off only at 1/r.
That's interesting.
Yeah. Okay, we can discuss that if you are around.
Yeah, I'll have to look at your paper.
Okay. So I have an announcement first, if there are questions. Eric?
I see no further questions. So yeah, I guess I should hand it over, but maybe I should also take the opportunity to thank the organizers before I hand over, because I'm the last chairman. So let me actually take the opportunity to thank all the organizers: Dimitri, Claudia, Alessandro, Donald, Pierre, Gabriele, and Sasha. So thanks for a wonderful conference, and I guess it's going to be continued by a workshop. So please.
Yeah. So thank you for this, but it was really a big pleasure. Now, of course, the conference week ends here, but not the workshop. And well, we have been a little bit slow in fixing the program for next week, but we are working on it. I can give you a little preview. Monday will be almost a free day, so we want to take a little breath and maybe meet personally in some way. But starting on Tuesday, Wednesday, Thursday, we plan to have a rather dense program again. And we are planning to concentrate the discussion on this PMS, symmetries, soft theorems, memory, and all that. So there will be 2 days of 2.5 days of talks, and then there will be at the end a general discussion, plenty of time for questions and for debate. Friday, we don't know yet whether there will be some extra stuff or not. So I only want to say, stay tuned. At the worst, on Monday morning, you will see details on the program, but I mean, things are going on. And okay, I wish also to thank all the speakers of the week for their brilliant talks. I think I personally learned a lot, and I'm sure many of you did as well. So, okay, have a nice weekend and see you next week.
See you.
Bye.
Bye-bye.
Bye.
Alessandra, I see you. Okay. Dmitry, did you have some other announcement?